Okay. So first of all, well, this is what I mentioned. You'll first hear me talking for 10 or 20 minutes or so about MOOS, basically what MOOS is. So MOOS stands for Multiphysics Object-Oriented Simulation Environment. So from a mathematical point of view, MOOS is just a PDE solver. It really is a mature partial differential equation solver that can solve a wide range of partial differential equations. And from a software point of view, MOOS is an extensible framework that integrates state-of-the-art scientific computing libraries for physics-based simulations. As we move on, as we build our own application, you will see that we integrate really a lot of high-quality scientific computing libraries, such as PETSI for linear algebra, LibMesh for the finite element function spaces, and many other high-quality libraries. And here is an overview of MOOS capabilities. So this is, in some sense, this is a inheritance diagram or dependency diagram showing the dependency among different MOOS capabilities. So at the very top here, this is the MOOS framework. I use this box to represent the fundamental finite element related capabilities inside the MOOS framework. So it is not specific to any physics. It's just everything common to a partial differential equation solver, basically. And then built upon the framework capabilities, we really have a very large gallery of so-called modules. So in MOOS terminology, we call them modules. So a module can be a specific physics module focusing on, for example, in our case, in this workshop, we will be focusing on the so-called solid mechanics module. And there are many other modules. The commonly used ones are the heat transfer module, the porous flow module, the fluid dynamics module, the phase field module, and etc. So other than these physics modules, we also have the so-called method modules. So for example, we have the paradynamics module, extended finite element method, XFAM module, as well as other helper modules. For example, the reactor module focuses on everything related to reactor, meshing, etc. And we also have the optimization module for you to solve inverse optimization problems. We also have the stochastic tools module for you to do uncertainty quantification and things like that. So for these, so all of the, so okay, so this list is not comprehensive. We have more modules if you go to the MOOS official documentation. But here you should have a high-level understanding of the structure of MOOS modules. And as you can see here, many modules depend on the solid mechanics module. So I would say it is fairly important for us to first understand how the solid mechanics module works, and then we can extend it to couple with other physics, the so-called multiphysics coupling. So all of these modules receive the so-called first-class support. So they are inside the big monorepo of MOOS. So for example, if you clone the MOOS repository from GitHub, you will readily get access to all of these modules. You don't have to do anything on your end. And for developers. So for example, if there is some physical phenomena or some other partial differential equations you want to solve that are not included in these first class modules, you will have to create your own application. And in this case, we refer to those applications as MOOS-based applications. Okay. And for example, in this workshop, we will actually create our own MOOS-based application from scratch. And then by the end of the tutorial, as I said, our application will be able to solve a multiphysics problem. Oh, and yes, okay. So I'm not actively monitoring the Slack workspace. So if you have anything you want to ask, just I guess leave a message in the Slack workspace and then shout it out and let me know, and I can answer questions. Yeah.
You mentioned that all of those modules receive first class support. So I assume they all have a set of verification problems, right, that are used to test, and that's what assures you that basically your installation of those is working properly, right? Can you say a little bit more about that?
Yeah, so for those of you online, the question was whether these, or the question really is for me to elaborate on the verification testing for each of the physics-based, for each of these modules, right? So, so actually in our agenda, in day 2, if you look at tutorial 13, I will actually tell you how to set up your own regression testing and documentation. But regarding your question though, yes, we have extensive unit testing as well as regression testing for both the frameworks as well as for each and every modules. They have their own set of unit tests, where unit test means that every single function works as expected. And then regression testing will make sure that all of the examples that we have set up so far do not regress as we keep doing our development. And we also have a set of verification problems, which is also an area receiving a lot of focus nowadays. And we are setting up a lot of verification problems to make sure the code works as expected. So there are 2 major ways of doing verification. We have a script to do a method of manufacture solution to make sure the solution is correct. We also do benchmark with existing codes that can solve this same problem or similar problems. Well, there are really a lot of testing capabilities there. Those 2 are the primary means of verification, I would say. There's also the Jacobian tester, which makes sure the implemented tangent stiffness is exact up to finite difference in precisions, things like that. I will cover that in tutorial 13 when we get there. But here, you can rest assured that it is our responsibility, is the MOOS teams and the physics modules team's responsibility to make sure every single object is working as expected and working correctly. Yeah. So next, I want to talk. About this frequently asked question, which is why we should choose MOOS over other software packages out there or other commercial softwares. So
hey, Gary.
Yes.
Hey, can I chime in for just a second?
Oh, hi.
I don't know if you can see my video. Hey, just regarding the Slack channel. So I'm Ben Spencer from INL, and I just want to let you know that I will be monitoring the chat and the Slack channel during this. So especially just to help Gary out with the people who are online who have questions. Just wanted to introduce myself. I did want to say though, I need to step out for the next hour or so. So I'll be joining back in a little bit later, but just wanted to let you know I'm here lurking.
Thank you, Ben. Oh, and that reminds me, I haven't introduced myself yet, because I was assuming many of you already know me, but for those of you, for those new friends online, and for those of you I haven't met before, my name is Gary Hu. I'm a mechanical engineer from the Argonne National Lab, and I also hold a joint position at the University of Chicago. So my primary work, my primary research focus is energy storage systems, such as solid-state batteries, thermal energy storage, things like that. My background is mainly finite element modeling. I graduated from Duke, from Professor Doble's research group, and I have joined Argonne for about 2 years now. So that's sorry about that. I totally forgot to introduce myself. Well, so let's move on. Yeah, why Moose? Moose is built upon those high quality libraries and packages. You can try it yourself. You can try to do your own research in this space and try to find the libraries you like, and most likely you will end up being at the same place as Moose currently is. So this really is the set of libraries that can best serve our needs as to developing a partial differential equation solver. So it is very scalable. So nowadays, scalability is everything. We have those very large supercomputers coming out every year. For many of the homegrown packages, as well as many commercial software packages, surprisingly, their scalability, especially for solid mechanics type of problems, is not good, I would say. I did a literature review once, and I found that for two of the arguably the most common commercial softwares, their solid mechanics solver can scale up to about 100 cores, and that's about it. If you go to about 1,000 processors, the scaling efficiency drops down to about 10% or so. So that's very different from Moose, though. We have tested the scalability of the Moose framework. It scales up to 30,000 processors with a very good both strong scaling efficiency and weak scaling efficiency. Well, so for those of you who haven't heard of these words before, weak scaling efficiency is a measure of scalability when you increase your computational resource and the problem size at the same time. And for strong scaling efficiency, it is you fix the size of your computational problem and you keep throwing more and more computational resources into it. And that's the so-called strong scaling efficiency. So my point is, for both of these common measures, Moose is doing a fantastic job there. And Moose and Moose-based applications have won several R&D 100 awards. So I think the most recent one is Cardino, which is a wrapper around several Moose-based applications. They won an R&D 100 in 2020 2023. Correct me if I'm wrong. There's another one called Bison, which is a moose-based application developed at the Idaho National Lab, heavily relying on the solid mechanics module. They won R&D 100 in 2022, I think. Well, and then the third bullet point there is, as I mentioned before, we not only have all of these modules, but we also have those moose-based applications, either developed by national labs or developed by university research groups or within the broader moose community. So most often, I mean, more often than not, you will find some moose-based application in the community that can already solve the type of problem you're interested in. And then it is often preferred if you can develop your application either based on the existing capabilities or you create your own fork, or it's basically a copy of the existing application. And then once you add the capability, the new capabilities you want, then you can contribute back to the existing application so that we have a growing community and list of capabilities. And also, Moose is chosen by the scientific community. There are over 100 active, unique contributors to the Moose code base, and there are over 500 publications. I think these statistics were gathered several years ago. Right now, I think we have much more than that, and we have more than 10 million regression tests run every week. So at this time, when I'm talking, we probably have several hundreds of regression tests running on the INL HPC right now to make sure all of the capabilities are working as expected. And then here is my little diagram trying to demonstrate that it's not only a very good tool that has been chosen by the scientific computing community, but also let's say if you're if you're from a company, you're from the industry, and your company wants to use Moose and wants to build or package your own Moose-based application. It's a very good interface, or it's a very good tool to connect developers and analysts. And by developers, I often refer to those people who can basically, in this context, write C++ source code. And then by analysts, in this case, I'm referring to those people who do not have background in coding, but have more expertise in setting up the actual physics simulations and doing analysis. And then oftentimes you will, if you're from the industry, you probably are aware of this issue where you sort of your analysts have to use some commercial software packages, and whenever you run into any issue, you need to contact the vendor, ask them for help, and then if there is an actual bug, you will need to wait for them to fix the bug and then wait for the next release. If you use Moose or Moose-based application, you don't have to go through that process. Your developers and analysts can work inside the same code base, and then the way to bridge the two sides is Moose, or the Moose parser capability, which allows you to compose or set up a simulation using the input file syntax that I'm listing on the right, without without digging into the details of the C++ source code. And then as soon as your developers make changes to the code base, you can go through the standard CI/CD procedure to deploy the set of changes to your analysts. So it's a very quick turnaround. Okay, so now we let me check if there's any questions so far. If not, we should start try to install get Moose installed into this machine. Okay, I don't see any questions on Slack. Yes. Yes. Oh, yeah, sure. So the question was, yeah, and hold on. So the question was, why should I use Moose instead of physics, like instead of Phoenix, right? Or some similar libraries out there. So for those of you haven't heard of Phoenix before, so Phoenix is a Python library which can solve, which is also a partial differential equation solver, I would say, using the finite element method. So I've also used Phoenix before. It's very easy to use. They have the so-called form compiler, which allows you to express weak form directly, and they will do just-in-time compilation for you, and they also use PETSI. So in that sense, it's fairly similar to Moose. And as I said, I've used both. I would say, I mean, right now this is recorded. I'm not sure if I should say anything bad about Phoenix, but I would say, in my experience, Moose has a very good documentation, at least compared to Phoenix at the time when I was using Phoenix. They probably have improved based on that. So that's number one. Number two, if you have well, so that's number two is related to how Moose is set up really. So you because in Moose you have access to every object you use during the simulation, and if you want to customize the behavior of virtually anything, you can do so, and you can do so very easily. Moose has a large number of systems for you to extend and customize. But in Phoenix, however, I often find it somewhat I find it less straightforward, let's put it that way, for me to modify some of the things I want. For example, if I want to solve a solid mechanics problem with an advanced constitutive model or material model, I can do that very easily in Moose. In fact, that's one of the tutorial I'm going to go over. But I'm not sure if there's really a directly supported way for you to modify the material update behavior at every quarter point in a library like Phoenix. So so that's number two. Number three is this idea about packaging your application. So I'm sure you have run into this scenario before, where someone in your group, in your lab or in your company, has have developed some capability based on some software, for example, Phoenix or Moose, and then maybe a few years later they left your group or they left your company, and whatever they developed becomes very difficult to access or to use. That scenario is different if you use smooth, which I will show you later on, because whatever object you write, ultimately it will get packaged into your application, and then everyone should be able to use this set of very easy to understand syntax, input file syntax, to use those objects instead of actually trying to read the source code line by line to get a sense of what it does. So that's number 3. That depends on 2 things, of course: good documentation and good testing, which I will also cover in this workshop, probably the second day. So that's 3 bullet points already. I mean, I can probably think of more. But I do want to say, if all you want is to solve a simple, well-defined partial differential equation, right? Using Phoenix is definitely a very good way to do prototyping, to test your idea quickly. I would argue, in that regard, it is easier to set up the prototype problem in Phoenix than in Moose. So that's my answer. Unfortunately, this is recorded. I don't know. I'll probably post-process the video recording. So the complete installation guide is available on the Moose website, but don't go there yet. I have summarized the set of installation instructions for you in the next slide. The recommended installation method is using Conda. It is suitable for both Linux and Mac OS. If you're on a Windows machine, however, we will have to let you install Moose inside the so-called Windows subsystem for Linux, and then follow the same set of instructions for Conda. And as Ben mentioned just now, if you run into any question, not just installation related questions, please feel free to post them in the Slack workspace, and some Moose developer will answer your question there. Or if you're here in person, you can raise your hand. I can walk over to help you troubleshoot any issue. So let's see how we want to do this. Let me for whatever reason, my mouse is no longer working. But anyways, I'll.
It's just that there's a lag. It's a little bit of lag.
Oh, there we go. So I'll try to follow these instructions on my side, and then maybe you can do this on your machine as well. And then let me know either ways. If you can successfully install Moose, let's say leave a message in either in the Teams chat, in the Slack workspace, or just let me know in person, so that I have a rough idea of how many people have completed this process. And if you run into any issue, please let me know. So meanwhile, I will do this on my machine as well. I guess let's see how we want to do this. Do you want to see this page open so that you can refer to this set of instructions, or you can open this open this set of slides on your own browser? I would recommend the latter. So let me So here's the link to these slides. So I'll post that in the Slack workspace, and you can open the slides in your own browser. So the workshop slides are available here. So if you follow this link, you should be able to see the same set of slides, and then you can navigate to the installation page and follow those instructions. Meanwhile, let me install it on my machine. So the very first step is to install Conda, initialize your Conda environment, and install the necessary dependencies. So once you have Conda installed, you can clone the Moose repository using the command I listed on the slide. So now I have Moose installed, cloned. I can create, what's the next step? And now we can go to the test folder of Moose and then type make-jn, where n is the number of processors you want to use to compile. So for my machine, since I have 20 cores in total, I will just be using 16 cores then. By the way, can you all read my screen, or should I make the font larger?
Probably a little larger here.
Okay. How about this?
Yeah. How do I tell my sponsors?
Okay, so now I have finished compiling my MOVE framework. I can run the regression tests to make sure everything is working as expected. And again, I think it's -J something if you want to run the regression tests in parallel.
What do you use for those tests?
So the question was what we use for testing. So there are many different testing methods. So I'll give one example. One way to do regression testing is you use the same input file to generate an output. In this case, I will mention that later. It's called Exodus. It's the format for storing the simulation result. And then then naturally we can have one type of regression testing by comparing the newly generated Exodus against a reference Exodus file. That is called exodif. So that's one type of regression test. Another type of regression test is CSVDIF, which is pretty self-explanatory by its name. And we have other type of testing. For example, we have the so-called wrong test or something, which just parses the input file and then make sure it can be wrong. It doesn't actually do any diffing against any reference. So you can read the related test harness portion of the MOVE's documentation to figure out what type of testing we have.
I'm not very
Oh, that's what you mean. So yeah, so for that we primarily use that for unit testing. So Google test is one example. You run a piece of code and then do some assertion to make sure the output is what you would expect. That kind of testing. Yeah, we have those unit testing as well. Yeah, that's actually a very good question. There's a subtle but important difference between unit testing and regression testing. Unit testing is you test every single function or capability or class in your code and to make sure the output is correct. And regression testing is to make sure your code does not regress. By regress, I mean, you know, if you have something working, but over the years, you make more and more changes to your code base, you add more and more new capabilities into the code, and you're no longer confident whether your previously working model can still work or not. Right? So regression testing is for that purpose. Okay, so at least on my machine, it shows that I have all of the available tests passed. Well, I guess I should wait for, I would say I'd wait for at least 50% of the attendees to complete this step, and then I will move on to the next step of installation. So as I said, if you reached to this point where all of the regression tests are passing for you on your device, let me know by leaving a message on Slack or in the Teams chat, or raise your hand.
Hey, Gary.
Yes.
Yes, hi. Sorry, I tried to remove the Conda environment and recreate it, and I ran into one issue which I posted on the Slack workshop channel.
Okay, I'll take a look.
All right.
think I run into the same issue. Conda cannot find these environments. Most developed environments. Keep trying to solve environment.
It's because concepts the way it would use an update and after we use a new
It should be on fine with this next. I have a problem. Question for you. So this is just trying to test the moves. Everything so far went okay, but it says it cannot find the lid mesh config.h.
So you have checked out moves, but you haven't done out.
Just follow the instructions here. So it did kind of contact, did this, it did activate. Right. And then I did clone. Right, let's see. Check out the master.
Did you always make changes?
Yeah. Yeah, you can look at history, right? Oh, maybe I did not.
You can do that again anyway.
Okay. All right, make sure that.
Yeah.
It's just exporting. I just telling you. I just saying you should see. And you're also from existing or here. Like a year ago, it's all the installation instructions just said to start using Mamba. And now Mamba's gone. Can't use contact. Mamba doesn't work.
I'll answer that question here. So so David asked the question. I think he asked. So 1 year ago, we were using Mamba for our installation process, but now we are suggesting Conda instead. What happened, right? That was your question. So just so you know, Mamba is a wrapper of Conda. So it's supposed to be a faster version of Conda, basically. And we've found that Mamba can solve the environment within seconds, while Conda usually need several minutes, or sometimes it's even stuck. But now it seems like that issue has been resolved, and many of the Mamba capabilities has been integrated into Conda already. So now we're recommending Conda again, but it's perfectly fine if you want to use Mamba or micro member, or there are many conda variants out there. They should work the same, I would say. Yeah. So for example, if you're using member instead of conda, just replace this replace the conda in these commands by member or whatever other environment manager you're using.
Is that Windows thing? That works. Yeah.
Even if they return Phoenix X, they can use parallel. At that time, it was
Gary, are you still recording?
Yes, but it's fine.
I was gonna say, Bruce versus Phoenix, I think the other big thing I would say is that Bruce has the advantage of having a national behind. Whereas I think in Phoenix is just kind of a community, right? But
I could say without actual researching with, I just say
yeah.
I mean it's really up to people.
Yeah.
Try out different techniques. You do have at some point you will we don't want to force people appreciate or something.
Yeah. I mean, the cluster group uses Phoenix, but they just ran into this issue with Phoenix X, where basically a lot of their old teams don't no longer run. So
Yeah, that's a common issue. Is a community maintain the package you don't have centralized. But because I work for them, so I don't know if they have any plan on improving that. I can't see that.
I guess the other thing would be the adaptive meshing. That's an option in Phoenix.
I think things only have triangular.
No, they must.
I'm sure they support walls.
But the adaptive meshing, I'm not sure if that's an option.
At least it was not in their own meshing function, but they can import.
Yeah, there is. But the matching for where the double attachment was, you modify the batch during specification.
I don't know.
I'd be surprised.
Yeah. No. Yeah. So Musi is built upon the branch, so that supports but there's more there's more issue to figure out before we support now solid mechanics. That's another challenge that you're aware of. For all those stateful material property reprojection and adaptivity, it's tricky.
Yeah. Gary, on the scaling with Moose, it's scaling well, linear scale or good scaling, weak and strong, 30,000 processors. What about hybrid architectures? Because if you like hybrid architectures, combinations of CPUs could also be tested.
Let me answer this question here.
So Professor Doble asked a very good question. So the question was, we talked about the scalability of Moose, but what about its scalability in terms of on hybrid machines where we use both CPU and GPU? So the quick short answer to that question is we haven't tested that yet. So we really need to understand the procedure of this PD solver, how this PD is assembled and solved to answer this question. So first of all, if you're familiar with the finite element method, there is an assembly step where you need to assemble your element, residue, and Jacobian into a large system of equations, right? So that procedure has not been vectorized yet, and so cannot utilize GPU yet. So that's I'm talking about Moose. And then once you have that system of equations, you need to solve it, right? So Moose uses PETSI or some other external software to solve the system of equations. PETSI, however, does support GPU. It supports actually I think all of the popular libraries, including CUDA and some others, and some other GPU implementations. And then there is the material modeling part. So for example, you solve the balance of linear momentum by equilibrating the stress. But first, you need to evaluate stress based on a given displacement gradient, right? So that procedure is referred to as material modeling or material update or constitutive update. That part is not vectorized yet within the Moose framework itself, but there is a external library called NEMO2 that's developed by the Argonne National Lab that can utilize both CPU and GPU. So putting everything together to answer your question, so we have three major parts. We have three different parts of this bigger picture. So we have the assembly, constitutive update, and solver. Two of them can already utilize GPU, and the only thing that's left alone is the assembly part, and that's being looked into right now. Yeah, I mean,
Okay, great.
and then actually as a spoiler, we've done some scalability testing for material models on their own. So for a simpler material model like linear elasticity, right? That scales well. So the typical picture is that GPU tends to be slower than CPU if if the number of updates in parallel is relatively small. So for example, if you have a mesh of 4 elements, 16 quadrature points in total, for example, it's not worth using GPU. That's the conclusion. But if as your problem scales up, becomes larger and larger, you have more things to vectorize or to parallelize. GPU will eventually become more efficient than CPU. And the final speed up is anywhere around 10 times to 60 times, depending on your CPU and GPU architecture. And for very recently, we added crystal plasticity support in MO2. And the scalability of that is surprisingly good. I think if the number of quadrature points is larger than a few thousand, then GPU is already faster than CPU, and then the final speed up is around like 10 times or so. That's speaking of like one single GPU, right? And then that's not trying to let GPU defeat CPU, right? So we can always use a hybrid architecture where we can utilize both CPUs and GPUs. So it'll be it'll simply add to your computational power. And for many of the newer exascale supercomputers, you have those hybrid nodes where you have every node is typically consists of maybe several hundreds of CPUs plus 1 or 2 GPUs. That's the typical architecture nowadays. I haven't got any messages on Slack yet indicating the progress. I hope everyone's doing fine.
Installation and testing might find on the machine.
Okay, cool. And then, by the way, yours is a Mac Silicon.
That did it the last year. So
Okay.
hopefully they don't
Okay. Is anyone using Windows?
Anyone using Windows? Not really run.
So
WSL. Yeah. Install WSL.
Okay, cool.
Yeah.
Okay. And then if you're using Linux or Mac, it should go fairly smoothly, I would say. Yes. Oh, you're from US? Yeah, so it's only fine. Yeah, you mean. So, I think the question was, can you install it on a remote machine? Well, right. Okay, so for this workshop, I mean, it's up to you, I would say. We won't be running any, crazily expensive examples in this workshop. So I would say a personal computer should work. But just to be clear, Moose works perfectly fine on HPCs.
Hello, Gary.
Hello.
Yeah. So I shared a screenshot on the meeting chat. I got hundreds of these pop-ups during current run test, And I got similar pop-ups when I was installing without Conda environment earlier on my Mac as well as HPC, not HPC. But I just wanted to know whether it is because of the VPN.
Yeah,
the network.
it is because of your firewall settings. And I think I don't know if Ben is online. He would be more helpful than I am in regarding this question. So when they install and run Moose at the Idaho National Lab, they also run into this sort of firewall issue. And the pop-up message is exactly the same as what you showed there. So hopefully he can chime in and answer this question. Let me see if I can get a hold of him.
Because earlier I was not installing via Conda environment because that is my preferred mode. But these pop-ups also used to come, and the problem was that it was not recognizing the MPI executive, MPI exec, means MPI run or whatever.
Yeah, I remember the solution was to add your local host name into the recognized host somewhere in your Mac. I just don't know the exact location of that.
Okay, so it will be good if you either connect me to the right person, or maybe tomorrow or maybe later in the meeting if he's able to answer.
Yes, I'm doing that right now.
Yeah, but they do run the survey here. Yeah, change that. So I guess.
Hi, Shashank. Do you mind if you can do you mind posting your question in the Slack workspace so that I can directly tag the person under your question?
Yes, I'll just copy that.
Okay.
Hey, Gary.
Sorry, 1 minute. Hi, Shashank. I replied you in your Slack post. If you have pseudo privilege, you can do the pseudo code sign for the compiled application. I think it's moose underscore test. I think I had a typo there, but try that. If it doesn't work, let me know.
So I will have to run the tests again.
Yeah, just for testing purposes. So after the code sign, you can run the test again to see if you still get those pop-ups.
Okay, I'll do it right away then.
Okay.
So it is moose underscore test underscore
Yes,
op.
yes, moose underscore test dash opt. Yes.
Oh, that is dash. Okay.
Yeah.
So this argument deep was not expected, it says.
Sorry, did you say anything, Shashank?
Yes, I'll reply there on the Slack itself.
Yeah, I think several other Moose developers are joining the Slack workspace to try to help you guys with any installation issues. So hopefully we can get that resolved soon. I see 4 or 5 people indicating that they have successfully installed the Moose framework. So just let me, so for those of you who have completed that, we can move on to the next step of installation, which is creating our creating the boilerplate code for our own application. That should be relatively straightforward once you have a working Moose. So first, let me go over the general steps. So, so if you have successfully installed Moose and all the tests are passing, you are now ready to create your own Moose-based application. So in this workshop, we will call the application Snail. So just for the record, usually when we create for as to the naming convention for Moose-based applications, we usually recommend people to name it after an animal, just to keep the convention with you keep using the same convention as Moose, I guess. And so for this workshop, we will call it Snail. To create your own application, go to the projects directory or wherever your Moose is sitting, and run the Stork script followed by the name of the application, which is Snail here. So once you do that, it should create all the necessary boilerplate code for you to start your own application. And for the purpose of this workshop, we've also prepared a set of additional boilerplate code for you to get things started, so that you can download it following this link and then unzip it into the same directory. So once you have that, the very last step is to enable the solid mechanics module in the makefile and then compile your application. So let me show you how that looks like. So here I have all of my Moose tests passed. I go to the parent directory where my Moose is sitting. I run the stock script followed by the name of our application, which is Snail. So this should automatically create a folder called Snail, containing all of the necessary boilerplate code for our own application. And so now we can use this command to download the additional boilerplate code for this workshop. and then unzip it. So now your own application should be ready to go. Though remember there's one last step, which is to modify the makefile to enable the solid mechanics module. So if you open the makefile using your favorite editor, and then so the file should look something like this. So by default, all of the MOOS modules are disabled. So remember, during the introduction, I mentioned there are many MOOS modules that's receiving first-class support. So in this workshop, we will just be using the solid mechanics module. So we changed no to yes for this module. Save the makefile, and now we are ready to compile the application. Again, type make j something. It should compile your application.
So this is the makefile in the snail directory.
This is the makefile in the snail directory, yes.
How different is usage of XFEM than solid mechanics portion?
Sorry, I didn't hear the question clearly. Can you repeat that?
Yes. So there is a module XFEM also at the bottom. So how different is it from the solid mechanics that workshop that we are having now?
Oh, so you're asking about this XFAM module, right? So
Yes.
yeah, so just to be well, so first of all, let's forget about MOOS, right? So that's I guess the first question is, what's the difference between XFAM and regular solid mechanics? I guess that's the first question. So so XFAM is, well, more strictly speaking, XFAM is a method instead of it's not related to any particular physics, right? XFAM is a method. It's a method to introduce enrichment into your finite element function space. Well, so anyways, solid mechanics is more concerned with the fundamentals of the balance of linear momentum and common solid material models. And the XFAM module is more related to the XFAM method itself, though it can be used in conjunction with the solid mechanics module to solve crack propagation or crack nucleation problems, yes. But more fundamentally speaking, it is a module for just a particular method. It's not necessarily related to the solid mechanics physics, right? Does that answer your question?
It's a natural extension of solid mechanics. That's why I asked.
Yeah. So, for example, if you want to build your application utilizing the XFAM capabilities, simply change this node to yes, and that will enable both solid mechanics and XFAM.
Yes.
Okay.
So means for me it is like if you simulate buckling of a cylinder, it is solid mechanics. If you are looking at the fractures in it, means because of extreme compression and non-linear dynamics of the compression, then it becomes XFEM. Means it's a natural extension of it.
So, well, so for buckling, yes. So either you solve a quasi-static problem or use the arc length method to solve a buckling problem, that should be related to the solid mechanics module. And for if you want to solve, if you want to study a crack or failure related to the buckling process, there are multiple methods to do that, and XFAM is one of them, right? And yes, and in that case, you should enable XFAM. And regarding structural dynamics, though, that is considered to be part of the solid mechanics module. So, for example, if you want to solve a wave propagation problem inside a solid media, that will be the solid mechanics module. Because for structural dynamics, you don't need any XFAM to be clear, unless you want to understand how a crack may propagate under a structural dynamics type of loading.
Okay. So my question is coming from somewhere else, because it has peridynamics also. So there is phase field method also as a module here. So I was wondering if solid mechanics is being solved through finite element method, then extended finite element method just incorporates new enrichment functions.
Yeah, so for solid mechanics, it is solved using the standard FEM. Yes. For XFAM, I know one way of implementing XFAM is by actually introducing enrichment to the function space. But the particular implementation we have for the MOOS XFAM module is using the so-called phantom node algorithm. So it's it breaks the element by keeping a phantom copy of the element, and then do numerical integration to resolve the heaviside enrichment there. And then for paradynamics, yes, that is a different. I would say that is another different method. And yes, many people use paradynamics to study fracture-related problems, for sure. And for the phase field module, that's so the phase field module by itself is more based upon the typical the phase field type of problems, such as void growth, dendritic growth, things like that. Although it can be coupled with the solid mechanics module to solve fracture propagation problems using the phase field fracture method.
Okay.
Yeah.
I just have one question there. If I have all modules, yes. So, and I'm for my application, I'm using only one, probably Navier-Stokes or solid mechanics, whatever. So, does it have impact on performance of the code, the app?
Yeah. So the short answer is no. Okay. So there will be negligible performance degradation if you enable all of the modules. There will be no runtime performance influence. However, if you want to enable all of the modules, there is a price to pay, which is compiling time, right? So you for your as a developer, you need to compile your application, and if you enable all of them, you need to go through the compilation process for each and every module. So that's something you have to pay. But if you don't really care about the compilation time, then I would say go ahead.
Yes, I did. Yes, and it took me like 5-6 hours to do that.
Yeah, and then so as a related note, some of the modules have dependencies among others. So for example, if you enable the heat transfer module, it automatically enables the ray tracing module by default, because some people may need to use the ray tracing module to calculate the view factor into certain geometry in use of a thermal radiation simulation. So that's just an example. So for example, if you set heat transfer to yes, then you are not only compiling the heat transfer module, but you're also compiling the ray tracing module, even though ray tracing module is set to no here. Just a note.
Okay, that makes sense.
Yeah, but for solid mechanics though, it's one of the base module, and so if you set this to yes, this is the only additional module we will compile. So here I have successfully compiled my base snail application. And again, we have the same test harness here. You can make sure everything is working as expected by the run tests command. So here we just have a dummy test here, the simple diffusion test. It's not really a solid mechanics test, but it's telling you that the testing framework is there, and the only one regression test is passing, which is a good sign. And then later on, we will dive into the tutorials and add more and more examples and source code into our application. And then if you want, you can add more and more regression tests into your own application. Okay, so this should be everything that's needed to do development for this workshop. And then there are some bonus points. For example, VS Code is the recommended editor for Moose-based applications, because we have some useful VS Code extensions to help with your development process. Although I would say feel free to use your favorite editor. Let's try not to get into an editor battle here. So if you are using VS Code, there are a few recommended applications to try out. The first one is the Moose language support, which I will you can feel free to install that now, but I will go over the capabilities of this extension later on when we actually write some input files. And then other than that, I would recommend the CLAN format. It automatically formats your C++ source code. And I also recommend the header source switch. So it allows you to switch between the header file, which is the .h file, and the source files, which are the .C files in Moose, using a command, using a keyboard shortcut. So these are really all that's needed. And as usual, let me know if you have successfully compiled the boilerplate code of our snail application. And then once I know most of us have completed that, we will start the actual tutorials.
Hi, Gary.
Yes.
So I tried that boilerplate code like in my previous installation that I had, like using that Mamba Force version. I think the not maybe latest version of the Moose. So it was not working. So then I uninstalled everything and installed from like your installation scratch. So now it is working. So is there like any specific reason that maybe
Yes. Yeah, that's actually a very good question. So that's related to the history of Moose, actually. So when Moose first came out about 12, 13 years ago, there was a solid mechanics module called solid mechanics, the same name as we see here. But several years later, since Moose was publicly released, we did a migration to improve the original solid mechanics module. And that migration created a new module called tensor mechanics. As some of you may have noticed, maybe somewhere in the documentation or in the workshop description or some other places, we sometimes refer to the module as the tensor mechanics module. However, several weeks ago, we renamed the tensor mechanics module back to the original solid mechanics module, and that probably created some confusion. And as you said, if you are using an outdated Moose, it may be only recognizing tensor mechanics as a module name instead of solid mechanics. And as a result, you may run into some installation issues. So that's why I recommend everyone to start from a fresh copy of Moose. But that being said, if you want to use an old copy of Moose, that should work as well, as long as you put tensor mechanics here. You say tensor mechanics equal to yes instead of solid mechanics. That's basically doing the same thing. That's my guess as to what's going on based on your description.
Yes, I think I got this thing. So are those like same, that solid mechanics module and like the previous tensor mechanics module, or like are there like any differences?
Right, they are the same. Though the original solid mechanics module was deprecated, and the tensor mechanics module is supposed to be faster. That's the improvement, and it should have. But in terms of capabilities, the current solid mechanics module should be identical to the previous tensor mechanics module. So you can think of it as a simple renaming. It doesn't change any actual capability inside the module.
Okay, thank you.
Hello, Gary.
Yes.
I wanted to ask you, so basically I didn't install whatever you recommended. I just went through the old version of Moose and I just changed to tensor mechanics.
Okay.
Going on forward from now for the workshop, everything that I will do, I just basically change it to tensor mechanics and it should be fine? Or is there something else that I have to do as well?
Right, I think that's all you have to do. So if you're familiar with tensor mechanics, you probably know that sometimes when we register and hold on. Well, let me type the code here. So usually you need to register. Hold on, let me think. Well, no, actually, I think from this point on, you don't need to do anything special. It ought to work out of the box, I think. But if you run into anything, any issue, let me know.
Okay, sure. Thank you so much.
Yeah, I think I saw several questions in the Slack workspace. So sorry for the confusion. If you're working with a outdated copy of Moose, for example, you already have a Moose installed, you need to say tensor mechanics yes in the makefile instead of solid mechanics. That's again due to the recent renaming, and sorry for the confusion. Okay, I think I will wait until well, so it's 10:50, 10:52 Eastern time right now. I think I'll wait until let's say 11:05. Let's give everyone another 13 minutes or so, and then I'll try to move on. But meanwhile, if you still have installation issues, please feel free to post it into the Slack workspace, and someone should be able to get to it.
So I have one question.
Yes.
So again, what do we plan to do with the boilerplate code that you have in there?
Yeah, thanks. That's also a very good question. Let me open my slides. So in this, as you can see in this agenda, so for these tutorials, for most of the tutorials in day one, we will be playing with different capabilities offered by the solid mechanics module, right? To do that, we will be creating input files and some source code inside our snail application. So that more or less serves as the code base for us to maintain the training materials. And then for day two, it's actually more relevant. It's necessary to use our application, because in this case we will be extending the solid mechanics, the standard solid mechanics capabilities to solve a multiphysics problem. And for that, we will be writing new source code. We will be adding, we will be creating new input files for our models. And then, so basically what we do in day 2 with Snail is not offered by the solid mechanics module itself. We will be doing something creative the second day.
Okay.
And then,
Thank you.
yeah, so yeah, and so for the as the final product, my goal is to let everyone have an application called Snail that's able to solve this phase field fracture problem. So that will be your own application. And then in principle, because of the license we use, it's you are free to make modifications, create your own application based on it, or package it, commercialize it even, and make profit, things like that.
Oh, thanks.
Okay, so I think I also received some questions in the Slack workspace related to the installation procedure. So Debanshu, I'm not sure if I'm pronouncing your name correctly. Can you are
yes,
you?
yes, you just pronounced it correctly.
Okay, so since you joined late, let me do a recap for you. So I assume you already have a copy of Moose installed on your HPC. So for this workshop, though, we will try to create our own Moose-based application based upon the Moose framework instead of directly using your Moose HPC installation. So for that purpose, you need to first go to the directory where your Moose repository sits, and then run this stark command here to create your own application called, in this case, called Snail. And then this will create a folder called Snail sitting parallel to your Moose folder. And then once that folder is created, you need to download some additional boilerplate code using this command here. So this is basically the training materials we have prepared for everyone. So if you download this and then unzip this inside the same folder, it should populate everything you need to get you started for this workshop. Okay, and
where do I find these codes, these lines? Are these in the slides you shared?
Yes, yeah. So so these lines are in the slides. I think I shared a link to the workshop slides. So this is, I think, page 4.3.
Okay, I got this. I got that slide. The slide is kind of 3-directional, so I got confused. Okay.
Okay. And then remember, once you have that, you need to enable solid mechanics inside the makefile. And if you are, in case you're working with an old copy of Moose, that's probably called tensor mechanics. Just double checking your makefile.
Okay.
And then once
so
you have
I can run that. I can run that Moose script stork.sh snail on HPC directly in parallel to Moose.
Yes, though.
Okay.
Yeah, I mean, depending on what your HPC admin says, usually, usually you need to grab a compute node in order to do heavy jobs. But for the starking and compiling, I guess it's fine if you want to do that on a login node or whatever. Just don't, yeah, don't overstep. Yeah.
Okay, let me try.
Hey Gary, so
Hello.
on my HPC cluster, what I had to do was so there was an installation of Moose already there.
Okay.
I could not store from there, so I had to module load Moose, then remove Moose and use all the dependent variables, dependencies to have a local copy of Moose for myself, where I can where I have writing privileges, because it was not able to make build directories, because it was trying to make build directories in the HPC module itself.
Yeah, so in that case, yes, I would recommend you to create. I would recommend you to clone your own copy of Moose in your personal directory on the HPC, where you have write access to, and then from there create your stock of Snail. Let me know if that works.
Okay, I could not work on HPC, but I could work on another workstation. There I ran the first code that was torque.sh snail. So I have created the folder. Now, do I use the curl command inside the snail folder or outside of it?
Outside the snail folder.
Okay.
And Pawan, I saw your question on Slack. You are receiving that you are seeing that because I think this is the tutorial boilerplate instead of the actual Stark. Did you successfully run the this command here, the moose Stark snail command? Make sure. Yes. So first run this command and make sure. Well, so first of all, remove what you have. Remove your existing snail folder. Run this command. Make sure. Make sure it creates a folder called snail inside sitting parallel to moose, right? So once you see that folder, do the curl command and then unzip. This should just unzip into the same folder called snail.
I see.
Yeah, what you're seeing there is just the workshop boilerplate. That's why you don't see the make file.
Oh, okay, sorry.
It seems like several of you are really close to getting this down. Maybe let's just wait for another 3 minutes until 11:10, and then we will continue.
Dr. Hu, I used the curl command. I unzipped it. Then I was trying to use the solid mechanics yes file, yes command, but it is saying that the command was not found.
Right. So that is not a shell command. That is so first you need to open the make file. So inside the snail directory, there is a file called makefile. You need to open that using some editor. And then in that file, there is a line saying solid mechanics equal to no. You need to change no to yes.
Okay, then I have to run the make J6 again?
Yes. So now if you, after doing that, you need to run the make command again in the shell, in the terminal. So this will, so this will additionally compile the solid mechanics module as well as the snail application. Right. So once that's done, you will have an executable. Well, so now that we are there, so after the compilation after the make J6 or make J command, it will produce an executable called snail-opt file for you. So this is an executable. So this is something you can actually run to get your simulation running. So if you invoke this executable in your terminal without any command line options, it should provide you with a list of accepted command line options. And later on in the tutorial, I will show you how to actually run a simulation. Okay. But I mean, my point is this is the entry point to everything. This is the final executable, not the compilation produces. Okay, it's 11:11 now, so we should move on, I guess. So first, I want to first I want to make sure everyone is on the same page by going over some of the framework level capabilities. So remember, in the dependency diagram I showed earlier, we have first of all, we have a MOOS framework, and then built upon the framework, we have different modules, including solid mechanics, and then building upon all the modules, we have different applications, including Snail, right? So the natural first step is to understand what the framework can do for us. So we do have MOOS workshop or MOOS training once every several months or so. So those workshops are dedicated to the framework level capabilities. But so in this workshop, however, we will try to focus on solid mechanics. However, I do want to go over the bare minimum of framework level capabilities just in case you are not familiar with the MOOS framework yet. So the MOOS framework comes with many systems. Each system is responsible for a very specific set of tasks. So, for example, the first system that I will introduce is called the mesh. It's the meshing system. So this first column in this table is showing the corresponding syntax that you will be using inside the MOOS input file in order to invoke that system. So this is mesh inside a square bracket. So this is just the entry point to define the partition of the physical domain where the problem is defined. And then similarly, we have other necessary systems for setting up a simulation. So I think you can find similar systems in other commercial softwares or other software libraries. They should resemble a very similar structure. But for MOOS, the variables block is for specifying the primary unknowns that you need to solve for in the problem. For solid mechanics applications, our naming convention is so first of all, we need to create the displacement variables, right? So those are the primary variables we need to solve for. Our naming convention is disp x, disp y, and disp z for the displacement. So that's disp underscore x underscore y underscore z. And then there's the kernels block. So these are the modular objects that define that actually define what's going on that physical domain. So mathematically speaking, these are the little terms in your weak form. So that's what kernels represent. And then we have the boundary conditions, initial conditions for setting the corresponding initial boundary value problem. The executioner configures how the problem is solved. So it tells us whether this is a steady state problem, a transient problem, meaning that there's a time integration being involved, and the solver options that you want to use. For example, should we use a direct solver, an iterative solver, how we are going to step through in the time steps, what will be the linear and nonlinear tolerances. Those are the type of things that we're going to include in the executioner block. And finally, the last block or system is called outputs. So this configures, this tells Moose what we want as outputs of the simulation. So well, later on I will show you in the tutorial. But basically, we can tell Moose to write a encoded file that contains the complete set of information about the solution to this problem for each and every time step, or you can do some post-processing to output some CSV files for further post-processing and things like that. So these are the very fundamental systems that everyone should be familiar with. And then this is what I call tutorial 0. It's not an actual tutorial that I want to go into details, but this demonstrates the basic Moose workflow for setting up a simulation. So first of all, you need to have a problem description in mind, right? You need to know what you want to solve using Moose or using the solid mechanics module. So in this case, let's say we have a specimen of this geometry. The bottom is fixed. The top, we're just applying the displacement control on the to simulate a uniaxial tension test, for example. The material is a neo-Hookean type solid with the two parameters lambda equal to 4,000, mu equal to 6,700. So this is the problem description in plain language that everyone speaks. And then you need to go through the step of translating what you want into the Moose input file. So, so here you can see familiar systems that I talked about in the previous slide. So the first block is mesh. So here it loads a mesh file to define the computational domain. And then this is the physics block that I will go into more details later on today. And then we also have the boundary conditions, materials, executioner, outputs. So this is how a Moose input file will look like for an actual simulation. So once you have this input file, you can use your application. So in this case, snail-opt. You can invoke that executable, pass this input file to that executable, and it will run this simulation. And then it will generate, so in this case, the output is exodus equal to true, meaning that we will output an encoded file in the exodus format. And then you can open that in using ParaView and then visualize the solution. So here is the animation of what's going on. Here I'm showing the evolution of the Vomisis stress, for example. So this is the general workflow for a Moose simulation. So I want to pause a little while here to make sure everyone is on the same page, because then we will start the actual content of the solid mechanics tutorials. Okay, no question is good.
Well,
yes.
1 minute.
Sorry. Let me answer one question here in person, and then I'll take any questions online. Sorry about that. Oh, you mean this input file? Yeah, that's a very good question. So yeah, the question was, why didn't we have the variables block in the example input file? That is because, well, so first of all, you can see here, I'm listing variables and kernels here, right? But you cannot see variables and kernels in this input file. Why? Because this physics block is setting up those variables and kernels for you. Yeah, so usually we are presented with a difficulty for communicating with analysts, right? So as code developers, we know what variables mean, what kernels mean for us, right? Because we actually write the code. But if you want to pass the input file to some people who are actually responsible for doing the analysis, they may not understand what a kernel means, right? So for them, it is easier to understand if you have a block like this, for example, physics, and then specify each and every physics you are interested in. And then it's easier for them to understand. And this block will automatically set up the necessary variables and kernels for you under the hood. Yeah, so for example, you can see there's a parameter here called add variables equal to true. So this will automatically add the disp_x, disp_y, disp_z variables for you, for example. And I think there was a question online. What was your question?
Yes. So, what all geometries can be imported into MOS?
What
you said Exodus. Yeah. So this mesh file.
Oh,
can it be
you mean
STL?
Okay, so you're asking about the accepted mesh formats, right?
Yes.
So this is one of the supported mesh format. Well, actually, I think I made these links clickable. So these are all links. But by the way, when you're viewing the slides, so the words in light blue, they are hyperlinks. You can open the corresponding link in your browser. So this will, for example, this opens up the mesh system documentation. And I think we have a list of supported mesh somewhere here. Yeah, so you see, MSH is the file I used in the example input file. We also support, well, the commonly used ones. Exodus, if you have a qubit license, you can easily generate Exodus meshes. DAT, MAT for MATLAB triangular ASCII file. We also have IMP for Abacus mesh format, and commonly used ones such as XDR, XDA, VTK, and PVTU, things like that. So it's I think it's a pretty good support. But if there's any file format you want us to support, feel free to open a ticket in the MOOS repository, and someone should be able to tackle it.
Okay.
There's
thinking of something like STL or
STL. Yeah, I would. Well, so first of all, is STL a mesh format? Yeah, I mean, you probably should create a mesh based on your STL file, and then pass that mesh into the MOOS simulation, I think.
Yeah.
So for example,
Okay.
I think I think both Gmesh and qubit support meshing based on STL files. Okay. Okay, so now we will start the official MOOS solid mechanics tutorials then. Well, it's 11:25 now. We are scheduled to have a lunch break at 12. So I will try to get through at least the tutorial 1, and we will try to finish the rest in the afternoon. We will reassemble at 1 p.m. Eastern time. So the very basic 1-slide summary of the theory of the balance of linear momentum, which is what we are concerned with for most of the solid mechanics applications. So we start from the strong form. Well, so for those of you who do not have too much background in finite element, so this is usually the governing equation that describes the physics. So here, this is the divergence of the stress equal to 0, and well, apparently I'm neglecting any body force, any inertial effects here, but I think you get the idea. So given the strong form, we can write down the corresponding weak form that we want to solve using the finite element method. So here we seek solutions to the displacement fields such that this weak form holds for each and every test function. And then once you have this weak form, you can apply the so-called divergence theorem to get the additional derivative onto the test function so that we can solve this with, for example, C0 finite element. Well, but anyways, this is the final weak form that we are concerned with. And this is what we will implement in MOOS. So to close this problem statement, we also need the definition of the so-called constitutive model, or some people refer that to as a material model. So those kind of models relate your primary unknowns, so in this case is displacements, to the forces that we want to equilibrate, in this case the stresses. So how you map from displacement to strain to stress, that's regarded as the material model. Okay, so does anyone want me to elaborate on any of the theory? If not, I will start the first tutorial then. Okay, so in this first tutorial, we will be writing some C++ codes. So I've set up most of the boilerplate codes for you. For this first tutorial, let us consider a very simple linear elastic material. The material model can be written in this form, where stress is equal to lambda, which is the Lemay's first parameter, times the trace of the strain tensor, times the identity tensor, plus 2 times the shear modulus times the strain tensor. And the strain tensor is equal to the symmetric part of the displacement gradient. And as a reminder from the previous slide, this is the weak form we're going to implement. So let's go ahead and implement this in MOOS then. So now open your favorite code editor, and then navigate to the snail directory. The first thing, so for this tutorial, we will be creating a kernel. So remember, a kernel is something that represents the terms in the weak form, right? So in this case, we will call it tutorial 01 kernel. So the header file will be sitting under include kernels and then the header file tutorial 01 kernel.h. The corresponding source file will be sitting under source kernels tutorial 01 kernel.c. Okay, so these are the two files we will be editing in this first tutorial. So in the first kernel, I have populated this boilerplate code for you. So so all of the kernels should, in one way or the other, inherit from the base AD kernel class or kernel without AD. So that's the kernel object provided by the Moose framework. We will be inheriting from the Moose kernel and then implementing our own weak form here. So you can see two methods here. The first method is input is called valid params. So this method defines what parameters we are expecting from the input file. And then this second method here is the standard constructor. It tells Moose how to construct this object given all the input parameters. So here, for example, we will create, we will add some parameters here that we want users to provide. So first, the parameter we want is the set of displacements. Well, whatever. So
Can you increase the font size?
yeah, I was wondering that. How do I increase the font? Okay, so we can, so in order to tell the input file that we are expecting the user to specify the displacements, we do params dot add required coupled var displacements. So this method expects two arguments. The first argument here is a string indicating the parameter name inside the input file. And the second argument is a string documenting what this parameter does. So this is, I guess we'll just say the displacement variables for this problem. And then the second parameter I want to add here, I mean, I may be coming back to add more parameters, but for now, I think I will ask the user for two material properties. Remember, the material model requires lambda and mu, those two parameters, those two material properties. So I will say add param material property name, let's say shear modulus of the material. And we also want lambda, which is Lemay's first parameter of the material. Let me think, do we need anything else? Probably not. So let's try this first. For documentation purposes, we will also want to add a string describing what this kernel does. So we will say add class description. So this is, I don't know, this kernel models a linear elastic solid. And then let me pause a little bit to explain what these parameters do. So for example, in the input file, hold on, sorry. Should I decrease the font a little bit?
Yes, please, don't mind.
Yeah. Okay, I guess this is better. How about this? So, so this set of, so these few lines tells Moose to search for input parameters that define this kernel. So, for example, this will be under kernels. The kernel will be called something like solid in X direction. Type equal to, well, I need to open a, yeah, how about this? So what this does is you will be creating a kernel in the input file. The kernel is called, for example, momentum balance in the X direction. So there is a special reserved parameter called type. So this tells Moose which object to construct. So this should be the object, the C++ object that we register. So this, in this case, it's called tutorial01 kernel. So Moose input file will know, okay, I should construct this object if it is requested. So the variable tells Moose which basically which variable this kernel is running on. So in this case, it should be disp_x. And then we need to tell this kernel what displacements we are using. So that's disp_x and disp_y. The material properties, that's shear modulus. So it can either be material property name or just a plain number. So in this case, I'll just use a plain number. In this case, I think it's 6,700 and lambda is equal to 4,000. And if you have the Moose language support plugin installed, when you save the file, it should automatically format your input file for you. And in fact, I need an additional parameter called component. The component of the residue to evaluate. So what this component does for us is, remember in the weak form or the comfort equation is a vector valued equation, right? So stress is a second order tensor. So the divergence of stress is going to be a vector. So the residue is going to be a vector of 3 values at every point, right? So that's what this component does for us. So this tells Moose which component this kernel is associated with. So this here, for example, I will say component equal to 0 for X. And we need to create a second kernel called Y, and that's the balance of linear momentum in the Y direction. We will be reusing the same kernel, but now the variable is associated with disp_y, the same displacement, same shear modulus, same lambda, and the component should be Y because now it's the linear momentum balance in the Y direction. So this will create the kernels for this problem, and in the source file, we have told Moose to search for these corresponding parameters. So for example, displacements. So now the Moose parser will tell us, okay, the user said the displacements are disp X and disp Y. And then the user has said, well, okay, the shear modulus equal to 6,700. The user has said the lambda is equal to 4,000, things like that. So that's how you connect between the Moose source code, and the Moose input file. So they should have a one-to-one correspondence for the record. So once you have, so the Moose parser is able to tell you the set of parameters that's parsed from the input file. Then it's your responsibility, it's the developer's responsibility to construct the kernel based on this set of input parameters. So here I will do that through the constructor. First, I think I want the gradient of displacements. So that's AD coupled gradients. Well, because we need the gradient of displacement to compute the strain tensor. We also want the value of the shear modulus and lambda. So I would say mu is get AD material property. It's going to be a real valued, it's going to be a scalar valued property. So it's that's real in Moose terminology. And lambda and finally component. Thank you. And then, so I would say as a developer, it's our responsibility to take into account what the user can specify from the input file. So for example, for a 1D problem, the user will just say, will provide only one displacement variable. For 2D problem, there will be 2 displacement variables. For 3D problem, there will be 3 displacement problems. But for Moose, we always consider we also do assembly conformal to a 3D formulation. So just for convenience, we want to resize the displacement gradients to 3 in order, just in case there's not enough displacement variables. So for example, if the user didn't specify displacement z for a 2D problem, then the gradient of displacement z will just be set to 0 then. So this should be enough for Moose to generate the corresponding documentation to tell users which parameters are expected for this object, and also it allows Moose to construct the correct object with the given user specified parameters parsed from an input file. Okay. And then this is C++ basic, but whenever you want to specify a member, you need to have the corresponding declaration in the header file. So we will create the these variables in the header file. Then for the gradient displacement, it will be a vector of a variable gradient. It's a constant pointer. And then for the material properties, they will be a it will be AD material property. And same thing for lambda. And finally, for the component, that's an unsigned integer. Okay. So now the most important method that we will implement in the kernel is how to actually compute the residue. So that will be AD real compute QP residue override. So we will be overriding the method provided by Moose. So this is the entry point provided by Moose for us to customize how a kernel computes the residue at each and every quarter point. Okay. So now we implement this kernel here. So it will be divided into 3 steps. Step number 1, we will compute, well, I think actually, yeah, there will be 3 steps. So the step number 1 will be computing the string. Compute string from displacement gradients. The second step will be compute stress from the string. The last step is to compute the residue from stress and the gradient of the test function. So for the step number 1, create a compute strain. That's by definition the symmetric part of the displacement gradient. So first, let's create a, well, for convenience, we'll say using R2 equal to AD rank2 tensor. So rank2 tensor is the second order tensor class implemented in Moose. So this will be G equal to R2 initialize from rows. So we need to tell Moose every row for this rank2 tensor then. So the first row will be grad this 0 at the current quadrature point. So underscore QP is an unsigned integer for the current quadrature point. So for example, if you're using a first order quadrature for a quad element, there will be 4 quadrature points. So underscore QP will be ranging from 0, 1, 2, 3, right? And similarly, we need to fill in the other 2 rows of the tensor. Oops. So that's grad this 0, grad this 1, grad this 2. The strain is the symmetric part of this. So G transpose plus G times 0.5. So now we have the strain. The stress following, well, just to remind everyone, well, maybe not. So the stress is just lambda QP times the trace of strain times the identity plus 2 mu times the strain, right? So this is like directly writing the mathematical formula in C++. And once we have the stress, let's look at so the weak form of the residue is just the weak form is just the gradient of the test function inner product with the corresponding row of the stress tensor. So for that, it's simply grad test times the corresponding row of the stress tensor. And that's it. That's all we need to do for this kernel. And once you have everything, the very last step to do is to register this kernel in Moose. So that is register Moose object. We'll be registering it to our snail application. The name of the object is called tutorial 01 kernel. And once you have the source code, you should be able to compile your application. So now your snail app will have an object called tutorial01 kernel, which is able to model a linear elastic material. And hopefully this can compile.
Hey, Gary, could you just scroll up in the kernel file?
Yes.
Thanks.
Okay. Now I'm getting an error. Oh, sorry, it should be gradius resize.
Gary, if you don't mind, could you share the C file somewhere in work or like just like to make sure?
Oh yeah.
Please. Thank you.
For those of you, well, so let me think about this. Well, okay, fine. I'll share with you all the answers for this workshop. So if you go to github.com, Hugary 1995 snail. So this is the repository for this workshop. So this is basically how our applications should look like at the end of this workshop. Okay. So if you go to this repository and well, it should have the same structure as what we have created just now. There should be source, kernels, tutorial 01 kernel, and you can see all the answers here.
Perhaps posting into Slack would be a good idea. Just yeah, thank you.
Yeah, okay. Yeah, so this is the repository. Yeah, so I think that's actually a good idea because you don't have to necessarily follow me line by line unless you want to really gain some experience in developing the source code. I mean, for you to try it out, you can just go to that GitHub repository and copy the corresponding tutorial answer into your own application and try to recompile your application. Although for tomorrow, I would recommend you to try to follow what I do step by step if you want to gain more experience in developing your own application. But for now, yeah, I think this is a good idea to because all we need here is to understand the basics of the solid mechanics module and how it works. Okay, so if you have everything now, especially now I've shared the repository with you guys, you should be able to get it to compile, hopefully. So once you got it to compile, we will, hold on. Now it's the time for us to write the input file for this tutorial. So that's tutorials 01. I'm calling it tension.i. And by the way, all the MOOS input files have suffix .i. And in this case, I've already added the two kernels for us. So now we have the source file, we have compiled the source file, and we have authored the input file. We're now ready to run the simulation, right? So in order to solve the problem in serial, you can use this command. So, well, the first argument is the path to the executable, which is snail-opt. The second argument is -i, followed by the path to the input file. And then if you want to solve the problem in parallel using multiple processors, just do prepend mpixec-n followed by the number of processors. Okay, so then it will run this problem in parallel. So, well, I do want to make a note here. Unlike other commercial software packages where they may be charging you for additional dollar amount for each additional parallel processor that you can use, MOOS is completely free. As long as you have a working MPI, you can run a problem with multiple processors with near perfect scaling. So the recommended way of running the MOOS models is to first navigate to the working directory of your input file, and then run your application. And then the name of the input file. So this will run, this will solve the problem for us. So at the very beginning, it gives you a summary of the simulation setup. So in this case, I'm using only one processor running the problem in serial. The mesh has 180 nodes, 153 elements. There's only one subdomain in the problem, and there are a total of 360 degrees of freedoms because here every node has two displacement variables, so in a total of 360 degrees of freedoms. The variables are displacement x and displacement y. The function space is from first order Lagrangian basis. This is a transient simulation solved using a direct solver. So now, so now MOOS will step through each time step, solve the problem, and then write the output into the, in this case, tension_out.e. So this is a Exodus file. And then the recommended way of visualizing Exodus file is ParaView. And if you haven't downloaded ParaView yet, I think I included a link here pointing you to the download page of ParaView. But once you have ParaView, you should be able to use ParaView. Or do I not have ParaView here? Oh, I probably don't have ParaView. Well, so I have to download ParaView on my for myself then. So go to the ParaView download page. Here I will just download the latest version of 5.12, 5.12. And if you already have ParaView installed, you can do ParaView tension _ out.e to open the file in ParaView and then visualize the results. So this concludes tutorial number 1. And then we will try to finish the rest of the tutorials in the afternoon. Well, so just to make things clear, we will only be writing source code in tutorial 1 and tutorial 2. So unlike other workshops, I put the most difficult part at the very beginning, and then later on we will just be modifying input files basically. So rest assured, it won't be more difficult than tutorial 01.
Do you have time for generic questions, maybe, or? Well, I know
yes, yes. I mean,
so
sure.
I noticed that. So yeah, just I guess some kind of silly question, but I noticed that when you create the name of the of this application with that script stork.sh, so. Yes. It converts all the capital letters to the non-capital letters, right? And then when you create the, like for example, when you added the kernel, right? So you would have to add the name of the, of the app exactly with capital letters, I think. So so if you created it and then forgot, what did you, like, which capital letters did you use? Is there a way to recover that?
Yes, there are multiple ways of figuring that out, but the method I use is usually I go to the source file base. You have your app right here. It's the lowercase s snail app.c, and you can see, I think somewhere here we're actually declaring this app.
Wait, where is that again?
Yeah, here. This is where we register the app. So it's called lowercase s snail app.
Oh, okay, I see. Okay, yeah, well, good to know. Yeah.
And hopefully, well, it's 12 now, so we can break for lunch, I guess, and we can reassemble at around 1 p.m. Eastern time. And meanwhile, I will, let's see, I will mute myself here, and I think I'll also turn off the speaker on my side. If you have any questions during the lunch break, feel free to leave them in the Slack workspace. And I don't know, if you're coming from a different time zone, this may not be lunch break for you. So feel free to proceed to the following tutorials. I mean, most of them are self-explanatory, and if you just follow the slides, and you also have all the answers in the GitHub repository, you can try to skip ahead and then do those tutorials, and also feel free to ask us any questions. Okay, with that, let's reassemble at 1. Okay, at this point, I hope most of you were able to compile the first tutorial.
Yes.
Yeah, okay, thanks. So just a quick recap of what we did in tutorial 1. So essentially in tutorial 1, we went from the mathematical description of the residual definition, which is the gradient of the test function times the corresponding row of the stress tensor, as well as the material model definitions, to the corresponding C++ definitions. And as you can see, the C++ source code we have in Moose closely resembles the mathematical equations. So for example, the string definition, well, it's basically verbosely first we created a gradient tensor, and then we compute the symmetric part of it to set that as the strain. And then the equation for the linear elastic material model is basically identical to the mathematical expression as well as the residual definition. So the real effort that you need to spend implementing this residual is just this 4 lines. So I would say it's fairly straightforward to do compared to many of the other C++ finite element codes out there. And there's one thing I want to make it clear at this point, because I feel like I didn't structure this workshop very well, in the sense that I probably put the most difficult tutorial as the first tutorial. So I feel like I'm giving you a false impression that Moose is somewhat difficult to use, and hopefully hopefully I can change. I mean, if that is your impression, hopefully I can change that when we get to tutorial 4 through tutorial 9. So basically, for tutorial 1 and 2, what I want to do is to go over the necessary steps to in order to basically create our own solid mechanics module from scratch, right? So for you to understand how the solid mechanics module really works, but in practice, you do not need to do any of this, right? So typically, if you want to just solve simple solid mechanics problems, you can just start creating your input file and then specify start setting up your simulation, and that's it. I mean, I would say 95% of the times you don't need to even open your source code in your code editor. Again, the tutorial 1 and tutorial 2 are mostly for everyone to understand how the solid mechanics module works behind the scenes. Okay. And also these 2 tutorials hopefully give you some idea of how developing inside the Moose framework looks like, if you intend to develop your own application in the future. Okay, so just to walk you through the input file for tutorial 1, these global, so there's a global params block. So this block defines common parameters in various objects, and they will well, so I think it's better explained by an example. So remember, in the kernel that we created for tutorial 1, we set displacements to be a required parameter, right? Because we need the gradient of displacements, and so in the input file, theoretically speaking, we should put displacement equal to disp x, disp y here in both of the kernels. We don't have to do that if we add the corresponding parameter in the global params section. So what this does is, for every object that we create, if it requires this parameter, it will automatically be filled with this value. That's what this does, basically. And then here we create a mesh by reading from a mesh file called sample.msh, is the Gmesh format. But you can equally well specify your mesh using the Exodus file format or the Abacus input format or any supported mesh format. And this block creates the two primary unknowns we want to solve for, which is disp X and disp Y. And these are the two kernels. Basically, they express the weak form that we are that describes this problem. And in addition, these two kernels also specify the material model, but I will tell you how to separate out the material model in the second tutorial. And then these are the boundary conditions. So in this case, I'm applying Dirichlet boundary conditions for both top and bottom. On the top boundary, I'm applying a displacement control, and it's a quasi-static simulation. And so I'm using the pseudo time as a parameter for me to ramp up the displacement on the top boundary. And then for executioner, I'm specifying this to be a transient simulation. So this is the so-called quasi-static simulation. Soft type equal to Newton. I would, so this is the recommended soft type for solid mechanics simulations, because now we have exact tangent stiffness for the material models as well as for all the kernels. However, I do want to mention that if your application, for whatever reason, if you want to couple more physics into your simulation, and for whatever reason you think it is difficult to implement the exact Jacobian or the exact tangent stiffness, there is another soft type called PJFNK, which is the full name is preconditioned Jacobian-free Newton-Krylov method. So the PJFNK method is supposed to give you a decent convergence, even if your Jacobian is not exact. So that's helpful in those scenarios. But for the solid mechanics module, I would recommend you to use soft type equal to Newton. And then these two these two lines are the options we use in the PETSI solver. So in this case, we're telling PETSI to use a direct solver, a direct LU solver, basically. Here we also set automatic scaling equal to true. So this option is very helpful because you know, depending on the unit system we use, for example, the materials Young's modulus may be on the order of 10 to the 9th or 10 to the 10th. In that case, is your the conditioning of your Jacobian matrix is not good, especially if you do multiphysics coupling. And so this option here, automatic scaling equal to true, will automatically apply scaling to each variable in order to improve the condition number of the Jacobian. But this option does not change this solution if your system is fully converged. And then here are these two lines describe how we should step through the time axis. So the end time is 2, and by default, the start time is 0. We step with a step size of 0.2. And the final block is outputs. We tell Moose to output the results in the Exodus format. And I think I didn't show you earlier because I forgot to install ParaView, but now I installed ParaView over the break, and I can show you how it looks like. So we've run the simulation, and it generated a file called tension_out.e. That is the Exodus file output. So this is how it looks like inside ParaView. You can select which variable to visualize. So in this case, this is the only variable we have. So it's a vector valued variable. So it has two components, X and Y. So let's look at its magnitude anyways. And then this is how how the specimen is deforming at the end of the simulation, and you can play the animation as well using this button right here. So it will play the animation of this simple uniaxial tension test. So that's basically how you visualize the result. So ParaView is more powerful than this. ParaView can also do some post-processing for you, well, which I will go into that in tutorial 3. But this should give you a overview of the workflow, hopefully. So now, if I don't see any questions, I'll move on to tutorial 2. Yes.
Are there cases where you wouldn't want the automatic scaling?
Yeah, so the question was, is there any case that you do not want to use automatic scaling? The answer is, I want to say no, because I mean, so now, yeah, nowadays I turn on automatic scaling almost for every simulation I run. Is there any? Well, so let's think about it this way. So what automatic scaling does behind the scenes is it tries to apply some heuristics to determine the scaling of each of the variables such that the ratio between the maximum Jacobian entry to the minimum Jacobian entry is as close to 1 as possible. That is different from minimizing the condition number. Right? The condition number is the ratio between your largest and smallest singular values or eigenvalues. But that is oftentimes a very good heuristic, right? But there will be cases where if you manually set your variable scaling, it may be able to outperform that heuristic, right? So I can imagine such cases would exist, right? But usually, I mean, yeah, this heuristics has worked for virtually all of the problems I've tried. And it really helps, especially when you have multiphysics coupling, when, for example, if you want to couple chemical reaction to solid mechanics, right? Your solid mechanics Jacobian is on the order of 10 to the 6 or 10 to the 9, depending on your material stiffness. But your chemical, the diffusivity of your chemical species may be something like 10 to the -4 or 10 to the on the order of tens. So in those cases, this automatic scaling is really helpful. Okay. Yeah,
hello?
I think I covered. Yes.
Hi Gary, I have a question. What about like something like as simple as Jacobi precondition? Because that also kind of diagonal, yeah, divides the rows by the diagonal. That also kind of makes every diagonal 1. What's the difference here? I didn't get it. Thank you.
Yeah, I sorry. You said which preconditioner? I didn't hear that clearly.
Yeah, the simplest one, Jacobi, which essentially you divide the system by the diagonal.
Yeah, the Jacobi preconditioner. Partially serves as as that purpose, yes. However, it's not going to be as effective as a full LU factorization for sure, because that's exactly solving the linear problem. I mean,
no, I mean for the, sorry to interrupt you, I mean for the auto scaling approach that you were just discussing, because that's also a scaling of equations and makes all the diagonal terms equal to 1.
Yeah, I mean, after, well, think about it this way. After applying the Jacobi preconditioner, it's not guaranteed that it's not even guaranteed that your reducing the condition number of the matrix. I would say conceptually, they might be similar, but I think they have different objectives.
I see. Thank you.
Yeah, I mean, so technically, there's nothing preventing you from using a different preconditioner. You can, for example, experiment with other preconditioners like Jacobi. But in our experience, automatic scaling plus a direct solver is always arguably the most efficient solver configuration. And so that is to there is only one drawback with the direct solver, which is memory limitation. For example, if for many of the toy problems, or sometimes we call it academic problems, we solve for maybe a few thousand or few hundred thousands of degrees of freedoms, a direct solver could work. But if you solve a problem that's larger than that, the direct solver may be too memory demanding given the amount of computing resources you have. And in those scenarios, we recommend we recommend a iterative solver. We recommend the hyper boomer AMG solver. I mean, we have documentation on that in the official website. Feel free to refer to those. But our experience is that either super LU or LU, the direct solver for small problems, or hyper boomer AMG for larger problems, those are the optimal solvers. And then I mean, in most scenarios, they outperform Jacobi. That's my experience. Okay, so those were very good questions. So now we can move on to tutorial 2, which is so the title is called Modular Material Modeling. So as we have seen, tutorial 01 kernel.c has demonstrated an elegant resemblance between most source code and the mathematical equations. However, I do see 2 places where we can improve based on what we have. So my first complaint is the source code we have in tutorial 1 works only for the linear elastic materials. It doesn't work for other types of materials. Say you have a hyperelastic material, or if you have an anisotropic material, the kernel we just wrote does not work. Can we generalize it to work for any material? So that's my first question. The second place where we can improve is at each quadrature point, the compute residue method is called twice or 3 times in 3D, well, 2 times in 2D, apparently. Can we avoid the redundant computations of strain and stress? Because, you know, when the residue in 2Ds, you know, it has 2 components, right? So we need to call the compute QP residue twice for in the X direction and in the Y direction for the balance of linear momentum. But due to the way we implemented the kernel, we included the material update inside the kernel itself, right? Which is computing strain and stress. So there's one redundant computation there, apparently. So we should think about ways of avoiding that. So the answer to both of these questions is yes, and we will be using the materials system to improve. So now you can open tutorial 02 kernel.h and tutorial 02 strain.h and tutorial 02 stress.h. Well, let me share my screen. Now if I open my editor, Okay, this is what we had in tutorial 01. So the material update as well as the residual definition is squeezed inside this compute QP residual function. That is, as I've explained just now, that's suboptimal, and we want to split it out to make it more modular. So if you look at tutorial 02 kernel, we will be overriding the same function, which is compute QP residual. And then instead of, well, so let me compare this to tutorial 01 kernel's header file. So as you can see here in tutorial 01, we have 4 members here: the grad displacement, mu, lambda, and component. So now in tutorial 02, we only have component and S, where component is the same. It tells us which component of the residual we are computing. The S here is a material property. Well, it's probably an abuse of notation. It's called material property, but really it's a quantity that is stored at each quadrature point. It's a rank 2 tensor. It's the stress at the current quadrature point, because that's theoretically speaking, that's all we need to evaluate the residue, right? So now if we go to the source file of the tutorial 02 kernel. So first of all, we register this object into our application. And I have the valid params and constructor filled out for you. So we need to define the compute residue method, compute QP residue. Again, let us compare that with the tutorial 01 version. So now all we need is this final line here. The gradient of the test function times the stress at the current quadrature point, retrieving its corresponding row. That's all we need for this new residue. So now we make a key observation here. This kernel now should work for any material, right? Because regardless of the material model you use, you will have to give us a stress, right? So once we have that stress, we will be able to evaluate the corresponding residual for linear momentum balance. So that's the idea. That's how we modularize this this whole thing. But now the question is, the kernel is modular now, but we still have to define the stress, right? So that we will use the material system. So if you go to include, so it's not subfolder kernels, it's subfolder materials. I have tutorial 02 string and tutorial 02 stress. So these are the 2 material objects that will define the linear elastic material model for us. And if later on, for example, if you want to add more objects to model different different materials, you do so by creating more and more stress calculators, right? Okay. So in the strain class, the only method we need to override is compute QP properties. And as the members suggest, we will be computing the strain based on the gradient of displacements. And same thing here, we will be registering this object to our application. And I have filled out input parameters and the constructor for you. Again, they should be identical to what we had from the tutorial 01 kernel. It's just now they are scattered around in different objects. Here we will override the string calculator. And you probably guessed what I want to do. I will just be copying from tutorial 01 kernel here because they should be identical. Oh, and I called it grad U instead of grad disp. Fine. Okay, and this should compute the string. Oh, by the way, we should be assigning the string to the material property here. So here, this API call, this declare AD property rank to tensor, it basically tells Moose that this material object will create, is responsible for creating a material property called string, right? So in the compute QP properties method, we should be assigning the correct value to the corresponding property, which is underscore E at the current quotient point. So that's how we would implement a string calculator. So now we have the kernel, we have the string calculator. The only thing left is the stress calculator. Same thing here. We will override the compute QP properties method. And here I have 4 members here. The first one is the string. So this is the string computed by the string calculator. And now I have 2 properties for the 2 members for the material properties, right? Because now the stress strain relation is only defined inside this object, and this is where the material properties should belong to. And this final member here is the output material property that this stress calculator should compute. Okay. And then if we go to the source file of the stress calculator, we register it to our application. And this is the necessary input parameters and constructor, very similar to what we did before. And again, we override the compute QP properties method. Again, I will just be copying from tutorial 01 kernel then. It's this line. So instead of returning this variable, we'll be assigning this stress to the corresponding property. Right, and it's the same definition. Now, if you want to, let's say you want to define a different material model for example, for some anisotropic material, all you need to do is to copy this stress calculator and then override this definition of the stress strain relation, and that's it. And then you can keep using the same string calculator, or keep using the same kernel, right? So that's the advantage of this modular design. With all this, I should be able to compile the application. And note that, oops. Oh, I see. So this is in tutorial 02 stress.c. It is complaining that E was not declared in this scope. Did you mean underscore E? This is a very helpful error message. So it'll be underscore E at the current port point. And same thing here. And I forgot to add the using R2 equal to AD rank 2 tensor Okay, so that compiled successfully. Now, if we go to tutorial 02, we haven't modified the input files yet. Go to tutorial 02. Okay, so now instead of, well, so again, I will be copying from the first tutorial. We should be using similar kernels, but now instead of tutorial 01 kernel, we should be using tutorial 02 kernel. The same variable, same displacement, but now the kernels do not need to know the material properties, so we remove them. Right, and how we define the material model then is through the materials system, as I mentioned in the slides. So we will say this is our I don't know, what should I call it? Linear elastic material type. Oh, sorry. So first we should create a string calculator. That's tutorial 02 string. Why doesn't it show up? Huh. And then once we have the string, we can create a stress calculator. It asks for the shear modulus and lambda. And that should be it. Tutorial 02 string is not a registered class. Did I misspell the? Oh, because I didn't say same f. I wrote here. So now I should be able to run this input. I think I called it mu instead of shear modulus, but let me double check. It's in tutorial 02 stress. Yeah, so as you can see here, I registered the parameter as mu instead of shear modulus. I don't know, I probably should have named it shear modulus instead of mu, but it is what it is, so I'll have to use mu here. If you change it to shear modulus here, well, so let me show you. If you change it to shear modulus here, then you will have to change the corresponding parameter name in the constructor as well. But for now, we'll stick with mu, I guess. It should run, it should converge, and it should give you the identical solution to what we get from tutorial 1. And same thing, we can visualize the output using ParaView. And yeah, this is what it looks like. And in tutorial 3, I guess a lot of you are already wondering at this point, how can we visualize the stress field or the strain field from ParaView? I will show you how to do that in tutorial 3. With that, I'll see if anyone has any question regarding the second tutorial.
Sorry, if I may ask a question.
Yes, please.
Sorry, so you mentioned prior to this that there are some solvers that are best for large multiphysics simulation. I think I missed that part. Could you please specify it?
Yeah, so the specific, well, so the preconditioner really, the effectiveness of the preconditioners really depend on the physics you're solving. For solid mechanics type of systems, hyper boomer AMG is the preconditioner that has worked the best for me at least. And we do have some documentation in the Moose official website on the hyper solver. If you search for hyper, does it show us anything? Or is it hyper? Yeah, it's hyper. So we have a whole page documenting common options for this preconditioning option. So, well, so let me show you how to specify that preconditioner in the input file. So instead of LU, you'll be saying it's hyper, and that's it. That's how you specify that preconditioner. And I think it's documented on this website as well. So this is a set of preconditioners developed by Lawrence Livermore. It's an algebraic multi-grid preconditioner, which has worked well for mechanics type of systems. So this is the this is the baseline configuration, hyper boomer AMG. And there are another 1,000 parameters for you to tune. And so for example, this is the set of solver or preconditioner parameters that's probably the most effective for many of the problems. And this should be a good starting point for you to start playing with using your own problem to see how you can improve the convergence of the simulation.
Thank you very much.
Okay. And I do want to point out, PETSI isn't the only option for solver. We can couple with other external solver packages. I know people have done that before. I mean, if you have your magic solver somewhere, you can probably post a question on the discussion forum, and we can tell you how to link moves to use that third-party solver. Okay, last call for questions on tutorial 2. Okay, if not, let's move on to tutorial 3 now. So as I've promised for this first day, tutorial 1 and tutorial 2 will be the only tutorials that require C++ coding. So from now on, we will solely be playing with the input files, which should be a lot easier for you. For tutorial number 3, as I mentioned just now, you were probably wondering how can I output stress or strain or other invariants like the Baumesis stress, hydrostatic stress, volumetric strain, deviatoric strain. How do I visualize those? So that's using a combination of material objects and post-processing objects. So as well as aux variable and aux kernel. I will show you some frequently asked questions regarding post-processing, and I'll show you how to set up the input file to do them. And then with a view towards tutorial number 4, the next tutorial, I do want to point it out that post-processing can get very complicated very quickly if you want to output a lot of components of a lot of tensors, right? so here in tutorial 3, what I'm showing you is the so-called brute force way of manually extracting every component of the tensor. And if we move on to tutorial number 4, I will show you how the solid mechanics module can simplify this whole process for you. Okay. Okay. So, anyways, for tutorial 3, the most commonly question I see on the discussion forum is probably, how do I output a specific component of a tensor at every point in the mesh so that I can visualize it, right? I mean, that's a very fair question. It's a common request. So we will be using the aux variables and aux kernel for that purpose. So, so remember, we introduced the two systems called variables and kernels before, right? So aux variables and aux kernels, they stand for auxiliary variables and auxiliary kernels. What auxiliary means here is they are not part of the system that is being solved for. They do not. I mean, they will not. They do not count towards the total degrees of freedom of your system, but they do they do follow the finite element interpolation procedure. You can specify a function space for each aux variable, and then we will do the interpolation for you. That's a 1,000 feet overview of these two systems. So in order to output a specific component of tensor, we'll be using this material object here to extract a specific component, in this case, the stress YY component of the stress tensor. We will use this aux variable and aux kernel to project the material property onto a constant monomial basis. What constant monomial means is it's different from a first order Lagrange basis, where it's it's a standard linear interpolation of C0 finite element. But constant monomial is element-wise constant function space. So what this does is it computes an element averaged property and set that value onto the as the elemental variable, so that you can visualize inside ParaView. This is purely due to the limitation of the Exodus format, because the Exodus format doesn't allow us to store information at every closure point. And so we will have to either store information at the nodes or the elements. And so we usually go with this constant monomial projection. And same thing, if you want to, for example, extract the XY component or YZ component of the tensor, just specify different indices here.
Sorry.
And for yes.
So there is no way to have a higher order auxiliary variable so showing the stresses on similar to the displacements, or
there are. So in fact, sometimes people do use first order monomial to do the projection, which it gives you a smooth field, at least, unlike a constant monomial, but it gives you a continuous field at least. Yeah, I mean that's user's choice. It's up to you which type of interpolation you want to use.
Thank you.
Okay, and then the next commonly asked question is, how do I output also tensor quantity or specific component tensor quantity now at a specific point, right? So if you compare to the previous question was asking, how can I output property at each and every point in the mesh? But now the second question is asking for a specific point. So we will be using the point value post processor. So we use the same material, same aux variable, aux kernel to do the interpolation, but now we add a post processor. So what post-processor does is you can think of it as something that extracts a single number out of the entire result of your simulation. So in this case, it extracts a single number, which is the stress YY value at point 550, okay, which is x equal to 5, y equal to 5, z equal to 0. That's what this post-processor does. The third question is, how do I output tensorial quantities such as strain and stress averaged over the entire domain? So that's a fair question if you want to do, for example, homogenization. If you want to, if you are simulating a representative volume element and you want to compute the homogenized strain or homogenized stress or something else, you will be using the element average material property or AD element average material property post-processor. So again, a post-processor is something that extracts a single number out of the entire result. So in this case, it is the average value of this property over the entire domain. And by the way, I haven't received any questions on what AD means. I assume everyone knows what AD is. If not, I guess I should explain here earlier rather than later. I'll explain that after this tutorial.
Hey Gary, one question.
Yes.
So in the average element material property, don't we have to specify the domain like block type or the block number or something?
Yeah, so that's a good question. So there's one parameter I didn't go into yet, which Pawan pointed out. It's called block. So imagine there will be cases in your simulation where you have a multi-material system, right? So part of the domain is material A, part of the domain is material B, part of the domain is material C, and you can have the same material model or different material models on those subdomains, or you can have the same physics or different physics going on in different subdomains. So that's completely up to you. And then that's so almost every kernel and material, they can be block restricted, meaning that, so for example, let me show you. For example, here, if let's say our mesh has two subdomains, A and B, then the disp X and disp Y will be by default defined on all of the subdomains. But if, let's say, one variable is defined on a specific subdomain, you can do something like disp X A block equal to A, if there is a subdomain called block A. So this is how you block restrict a variable. And you can do the same thing to block restrict a kernel. You can say block equal to B, which means that this kernel is only active on the subdomain B. You can do the same thing for every kernel and as well as every material. Now the question is, can you do that for the post-processor? Yes. So here in post-processor, let's say I want to get the average stress over a specific subdomain. Let's say block equal to AB. Because for whatever reason, I may be having three subdomains, A, B, and C, and I only want to compute the average stress YY in subdomains A and B. This is how you do it. But if you omit that parameter, by default, everything will run on the entire mesh. That's why you don't see those block options in my example input files. Does that answer your question?
Yes, thank you.
Okay.
Hi, Gary. So that average strain that will be calculated for the each element, so that will be like then again interpolate it to the all the nodes using like those auxiliary thing?
No. So if you're curious about what's going on behind the scenes, the element. I mean, the name of this post processor is probably confusing. It's not doing an element average. It is looping through every element in the domain. It computes the integral. It computes the domain integral of the specified material property, and then divide the integral by the domain volume, the total volume of the domain. So, and how do you do numerical integration? You use Gauss quadrature, Gauss quadrature or whatever quadrature rule you specify. And so what it does behind the scenes is it loops over each and every element, and on each element it loops over every quadrature point. And at every quadrature point you have a value of stress YY stored there. It will perform numerical integration. It will execute the same routine for all the elements, and then sum them up to get the total integral, and then divide that by the total volume of the mesh. So that's how we compute the domain average, the material property. I mean, the name of this object is probably confusing or misleading. It may be better named as something like domain averaged or something like that.
Okay. And so can we get also like those quadrature point stresses as output like in a other text file or CSV file?
Yeah, for that purpose you have to. Well, actually, that's a good question. I mean, technically speaking, there's nothing preventing you from doing that. So what I'm not sure about is whether we already have an existing post processor that can do that for you. I'm not sure. I need to go back into the documentation to check. But what you described is definitely possible. Yes.
Okay.
So you're basically asking, can we output the result into a file with format like, for example, a CSV file with, coordinate XYZ as the first 3 column, and then the value of the property value at the corresponding quadrature point as the 4th column. That's possible. Yes.
Hey Gary, can I chime in?
Oh yeah.
So that's we do have. This doesn't really give you what you want, but those aux kernels that output components of the stress tensor, some of those have an option in them that allow you to output a certain quadrature point ID, but that just shows up as the value for the whole element. So it's really not that great. And I've long wanted to do exactly what you're saying, like have dump them all out to a CSV file. I think that would be a good thing to do. We just haven't gotten around to it.
Thank you.
So I guess kind of a follow-up question to that. So because this is a one value for probably like one time or something like that, and if we have some kind of a transient problem, right? So we have the value of the material that evolves in time, and for example, when you have many points, or I don't know, perhaps some kind of block of the I don't know, basically not just one number, but some kind of more complex data structure. So what would be the also the format for that as a result of the post-process? And perhaps it will be, I mean, I don't know. So I guess you guys just answered that you kind of in the process of developing it, but it would be nice.
Yeah. So that's I think you really asked 2 questions. For first, what happens if this is a transient simulation, right? So let me just run the input file and you will understand that part. Okay, so as you can see, so by default, all the post processors are being executed at the end of each time step. And so what you get in the end is a CSV file with the corresponding columns for each of the post processor, and then the values for each time. Okay, and you have finer control on that. That is the execute on parameter. As you can see, the default value is time step end, but you can also say, I don't know, time step begin or final or failure, or something like that, or linear, non-linear. You really have more control over that to tell moves and to perform the post processing. So that should answer your first question. The second part. Yeah, the second part of your question, you were asking if you have some advanced data structure and how do you output that. I would say that's up to you, because you know, the MOOS framework does not know what data structure you're going to use. I mean, so the MOOS framework does provide post processors for the native data structures we have. For example, RAM2 tensor, we know how to output them at every closure point. But if you have some complicated data structure, then that's a valid scenario for you to write your own post processor. And you can easily follow, for example, this some of the existing post processors. So basically, what you will need to do is to override the corresponding method. I think in this case it's called execute or something, which will be called at every element for an elemental post processor, and you will write in C++ how you want to extract that single number from your complicated custom data structure.
Oh, that's excellent, actually. But then the location of this, let's say, example of the or whatever post processing, are they located in the in this model that, or I guess the model that we are developing or creating, or it is somewhere in a source code of the main source code of the whole software?
Yeah, I mean, you guys are always asking very good questions. Well, so regarding examples, there really are two places to look for them. If you are, let's say, if your role is more like an analyst, where you will primarily work with input files, this MOOS website is your go-to place for documentation, where if you go to documentation, syntax index, you can see a list of available objects for that's available to you. And I think they are also grouped by physics modules. And if you go to post processor, which is here, you can see a list of available post processors. And then, for example, if I open AD element average material property, it will show you the set of input parameters that MOOS is expecting. And it also shows you all the relevant input files that that are using this object. So this should be a good starting point for you to understand how to structure your input file. And now regarding examples for the C++ source code, you have well, so the place I would recommend you to go to first is the MOOS repository, because it's fully open source. You can always open the corresponding source code and see what they do over there. I think it's, in this case, it's element average material property. And you can see the execute method. It gives you the it first computes the property value at the corresponding closure point, and integrate that, and finally divide that. Oh no! So here it also integrate the volume, and then finally, when we return the value, we return the integral value divided by volume. So my point is, if you want to get an example of how to implement your own object in C++ in your own application, the Moose repository is a good place for you to start. And we also have the complete set of Doxygen documentations, not to mention. So again, navigate to the Moose official website. There is this framework development tab, and we have the Moose Doxygen and module Doxygen. So these are the classical way of documenting code using Doxygen. I don't know how familiar you are with it, but you can find all the necessary APIs related to each object. For example, AD material, sorry, AD element average material property. So this tells you, this gives you the, well, so first of all, which objects does this AD element average material property inherit from, and then the set of APIs you can use in your custom material. So that's how I usually do when I want to implement something on my own.
Oh, great, great. That's I mean, Doxygen is amazing. Actually, the last question. So, if you, for example, develop your own this post-processing thing, so you copied the you know, source code from the you know, from the main repository. So you modify the expression that you want to calculate, I don't know, like multiply by 2 or something. So, and then when you want to execute that one from your application, do you have to create a third application that to compile a post processor there, or basically it will be a part of your application? So I mean, when you store the files and compile them, I don't think you do that in the main repository, right? So you do that within some kind of external place, right?
Right, and for this workshop, Snail is the place, is that third application you mentioned, basically.
Okay, good. Yeah, thank you.
Yeah, so basically in this workshop, we have already created some custom materials and kernels already, and we've registered it to Snail, which is a Moose-based application. And as you can see, we can use them in our input files just fine. So
good.
Yeah. Okay.
That makes sense.
Same thing applies to post-processing, yes.
Yeah, thank you.
Okay, let me know if there's any other questions related to tutorials 1 through 3. If not, I will move on to tutorial 4.
Dr. Hu, I was looking at tutorial 3 and looking at the force that was post-processed. The variable ry was taken from tutorial 2. I got a high-level understanding of how the steps were taken, but can you just maybe go through with a few lines, like the steps, like how the ry was taken from grad test? What does it mean? Just give a very high-level idea, like in few lines.
Yeah. Sorry, I forgot to go through these 2 last slides in tutorial 3.
Yeah.
I totally forgot. So
the fact is, we got the equations and stuff, but when I'm looking at the input file only and looking at the .e file, that is the Exodus file in Paraview, I was trying to visualize that what is coming from what. So it would be great if you just give a few lines so that we can connect the property.
Yeah. So for context, in order to extract the total reaction force, we need to first know the reaction force corresponding to each and every degrees of freedom. So, I mean, from a mathematical formulation point of view, whenever we apply a Dirichlet boundary condition, so here in this tutorial, for example, we have the boundary conditions are Dirichlet boundary conditions on top and bottom, right? So when you have Dirichlet boundary conditions, you are setting the values of those the corresponding degrees of freedoms directly instead of solving for the system of equations. And so the residue at those degrees of freedoms will not be zero. And those non-zero residues are the so-called reaction force in the context of mechanics. And in order to compute the total reaction force along a boundary, that is as simple as summing up all the nodal reaction forces together along that boundary. And then the final question is, how do we extract the residues corresponding to the degrees of freedoms where we have Dirichlet boundary conditions? That is using this save in option. So it basically saves the residual value at those degrees of freedoms into these aux variables, right? And so an implicit requirement would be the aux variables should come from the same function space as your primary variable. So in this case, if your displacement x is first order Lagrange, then Rx should be first order Lagrange as well. Same thing applies to this y and Ry. And so this Rx and Ry, if you open up the result in ParaView here. So if you open tension.e inside ParaView and look at Rx, for example, or Ry, you can see the values of the reaction forces, nodal reaction forces, are zero everywhere except where we apply the Dirichlet boundary conditions, and that's what we refer to as the reaction force in the context of mechanics. And what these post-processors do is simply summing up the reaction force together along the top boundary so that we get the total reaction force for that boundary. Did I explain that clearly? Hope.
Yes, I was trying to see where the Rx was processed. I'm seeing force as Ry, but in the Exodus file in ParaView, I'm also seeing Rx. So
Rx is the nodal reaction force in the x direction. Yes.
Okay, I got it. Sorry, the post-process is saved in the CSV file, and the auxiliary variable is being displayed in the Exodus file. Okay,
Correct.
Okay, I got it. Thank you so much.
Yeah, that's a very important point actually. So if you look into your look at your ParaView interface, you can see these so-called block arrays, or I think the naming actually depends on your ParaView version. So these arrays with 4 dots on them, those are nodal variables. So those are information stored at every node. And then this one, it looks like a hex 8 element. It's the elemental variable. And for the post-processor values, I think I don't see them here. But you, in fact, you can plot the post-processor values using this button here, plot global variables over time. It will show you the list of available post-processor values. So in this case, let's say I want to plot the force displacement curve. This is it. And as it's expected, it's a linear because it's a linear material. So it means when the average displacement is equal to 2, the reaction force is about 26 Newton per millimeter, actually. So, okay. but these values are being stored in the CSV file as well, as you can see here. Okay, now let's move on to tutorial 4, if we don't get any other questions. Okay, so as a recap, in tutorial 1, we implemented the balance of linear momentum weak form inside the kernel along with the material. We improved the structure to make it modular in tutorial 2. And in tutorial 3, we went over a set of frequently asked questions on post-processing. And now we have effectively implemented the our own solid mechanics module inside the snail, right? So that should give you a fairly good overview of the implementation of the solid mechanics module. And now I think we're ready to learn what the Moose solid mechanics module can do for us, right? So so here I have a bullet point list. It can automatically create variables, kernels, and string calculators for you. In fact, I think I got one of the questions from you guys. I've explained this already. It can also simplify tensor outputting for you. So for example, from tutorial 3, we don't want to do this for each and every we don't want to do this for each and every variable, each and every component of the stress tensor, strain tensor. That just inflates our input file. We want some way to of simplifying that, and that's what the solid mechanics module can do for you. It can also it also has a gallery of commonly used material models, be it small deformation models, large deformation models. It can do volumetric locking correction for standard stabilization purposes. It provides a other material models such as plasticity, that is a common type of material material model. Viscoplasticity, creep, damage models, and so on. And at the end of today, I will also go through a list of other advanced features, such as homogenization, factor integrals, cohesive zone method, and etc. And if you're interested in any of the advanced features that I'm going to just briefly go over at the end of the day, feel free to leave a message in Slack, and we can discuss in more details. But for now, for tutorial 4, I will just show you how the solid mechanics module can do the first 2 bullets for you, which is automatically creating variable kernels, string calculators, and simplify tensor outputting. The canonical entry point for the Moose solid mechanics module is through this physics syntax. So basically, in the input file, you need to write physics, and then a nested block under physics called solid mechanics. And under solid mechanics, there should be another level of nested block called either quasi-static or dynamics, depending on whether you're doing quasi-statics or dynamics. And so let's go over this. Well, actually, I think I have this here. Yeah, I have the input file here to show you how this physics syntax looks like. So remember, from tutorial 3, we still have those. Well, let me open the file. From tutorial 3, we still have those variables that we manually created, the kernels for linear momentum balance in X and Y directions, as well as the strain calculator here. The in our case is the small strain definition for implemented in tutorial 02 strain. And we also have this helper material to extract a specific component of a tensor, as well as the post-processors to post-processing. So most of this can be done using the solid mechanics physics syntax, which is shown here. So everything else in the input file should stay the same, except the corresponding blocks I mentioned just now: variables, kernels, and string calculator. So the correct set of variables will be created based on the problem dimension. So for example, if you have a 1D problem, we will automatically create this x. If it's 2D, this x, this y, 3D, this x, this y, this z. If you set add variables equal to true. If you set add variables equal to false, we then don't do the physics syntax doesn't do that for you. You have the option of creating those variables on your own. And now we will create the correct string calculator based on this string equal to small or string equal to finite. Well, small is for small deformation, finite is for large deformation. And we have two formulations. The first one is the so-called total Lagrangian formulation, and the second formulation is the updated Lagrangian formulation. It's basically updating the model in different intermediate configurations. And then these are the most useful part of the action, which is setting up all those aux variables, aux kernels for post-processing purposes. So let's say if you want to get the 6 component symmetric stress tensor, this is what you will need to do. Say Cauchy stress, x, y, z, xy, xz, yz, and same thing goes to string. Well, we call them mechanical string in our terminology. And if you want to do additional element-wise quadrature point-wise post-processing to extract some additional output. So for example, if you want to compute stress based on the stress tensor, this is what you will do. Or you can say other things like hydrostatic stress, max principal stress, or mean principal stress, things like that. So it will create the correct objects for you automatically. Okay, now let me try to run this. So the idea is if I just add this block into my input file, we should be getting the same result as tutorial 1 and 2. Yep, and then feel free to examine the results on your own. And there are actually better ways of making sure the results are same compared to some reference outputs. I will cover that as part of the regression testing. But I think now you get the rough general idea of how to what the solid mechanics module does for you behind the scenes, because technically speaking, we have created our own version of the simplified version of the solid mechanics module. Yes. If you say total here, it's total formula. Yeah. Well, I mean, that reminds me, that's a good question, because we have this new system equal to true here. For I mean, for new users, you don't need to worry about this. But if you are if you have previously used the tensor mechanics module for some of your simulation setups, you probably want to learn what this new system does for you. And I have a comparison in the next tutorial to demonstrate what we can do using this new system with objective integration, for example, hypoelasticity. But the bottom line is the new system should be able to do whatever the old system can do. It can do things better because it provides you with the exact tangent stiffness. As some of you may know, the old tensor mechanics module weren't able to provide the exact Jacobian for some of the convoluted material models, but the new system can. And the new system also provides you with additional ways of performing objective integration. So the old system uses the Rashid implementation from, I think, 1993. The new system provides you with 3 different ways of doing objective integration: the true star rate, the Yeoman rate, and the Green-Hardy rate. And the Yeoman rate is probably what Atlas uses. You using MOOS, you can very easily switch among those different objective integration methods. Anyways, I'll go into more details in the next tutorial. If we don't have any other questions regarding this tutorial number 4, the physics syntax, I will move on to tutorial 5.
Dr. Hu, probably you will talk about this in the later tutorials, but I was just asking that, let's say if I want to change any parameter in one of the outputs, like if I want the strain to be calculated differently, but still I'm trying to use the solid mechanics other source codes, is there any way to just add a single kernel that will override that one equation?
Yeah, I mean, that depends on what you want to do specifically. If you want to modify the string calculator, that is actually a rare request, I would say. If you want to modify how the string is calculated, you will have to basically unroll this physics syntax to go back to the expanded syntax from tutorial 3, for example. So, yes. For example, you have to spell out instead of using the physics syntax. But let's say if all you want to do is to create a custom stress calculator, right, then you can use the physics syntax, because, well, here I'll show you. If you remember, I said that the physics syntax creates variables, kernels, and string calculators for you, but it doesn't create stress calculator for you, because we know people will want to use their custom material with custom stress string relationship. And so here we still have in the materials block, we still are defining a linear elastic material as a placeholder, but you should feel free to replace this with whatever material model you want to use.
Okay, so if I understand correctly, the physics is kind of describing the strain, which should be constant for any system, but we are changing the stress, which will depend on the material or the system we will use. Am I right? Okay.
Right.
Okay, great. Thank you.
Yeah. Regarding strain, I know some of you may argue that strain can be coupled to other physics. For example, thermal eigenstrain is a common thing, right? And you may have other eigenstrain, for example, swelling from chemical reactions. That's also a common one that requires modification to strain. That's possible with the physics syntax, though. That's the eigenstrain system, which unfortunately I don't have time to go through in this tutorial, but that's possible. I think it's just an additional parameter here called, yeah, you just say eigenstrain names, for example, if you want to say thermal eigenstrain, and then in your material, you will define your own thermal eigenstrain, and then the physics syntax will respect that. But if you have a chemical eigenstrain, you can do that as well. You just need to define your own material property with name chemical or with name thermal, containing the value of the eigenstrain. If that's what you mean by modifying the strain calculator. So just in case that's what you mean. I think the video you have a question.
Yeah. For the new system, and take it with the, is it only available to use the physics block? Can I define it as a user system by just define particles individually?
Yes, that is always an option. So with physics syntax, you don't only have solid mechanics, there will be more physics added in the future. And for every of those physics, you can always fall back to the the expanded version of the input file. You always have that option. But I would say it is your responsibility for selecting the correct string calculator and kernel and such. Okay, now let's move on to tutorial 5. And again, we don't need to write any source code for this tutorial. Okay, so the solid mechanics module makes switching between kinematics a trivial task. Well, you saw this parameter here, string equals small here, that tells Moose solid mechanics module to treat the problem with small strain assumptions. If you want to switch to a large deformation formulation, just say string equal to finite, it will create the correct kernels and the string calculators for you. So in this case, well, so if you so as common input, we will create a material property called deformation gradient. If you want to use that for hyperelastic formulation, we will create a material property called strain increment. If you want to do hypoelasticity formulations and things like that, you can read the Doxygen documentation for details. Large deformation formulation comes with two flavors: the so-called hypoelasticity, which basically which basically advanced a small strain definition along with your material frame to render it large deformation. And there is also the standard hyperelasticity formulation, which is usually derived from a strain energy density or potential. Yeah, I would say depending on, I mean, right now, I feel like in the US, probably 50% of the universities are teaching hyperelasticity and the rest are teaching hypoelasticity. So this is what we did for you. If depending on where you came from, you may find one of them more familiar. That's our hope. And so let's compare 6 different elastic material models in this tutorial. So, well, this is also a demonstration showing that it's very easy in the most solid mechanics framework to switch among different material models. I'll show you in a second. All you need to do is to modify the 1 or 2 material blocks. So for small deformation, we've already seen. We've actually coded our own small deformation model, but there is indeed a Moose native linear elastic material model there, which is just a linear mapping between stress and strain. For large deformation, hyperelastic formulation, we have some common hyperelastic models just as examples. I know even for St. Vernon-Kirchhoff, it's the expression is pretty standard, but for Neo-Hookean, depending on if you're looking at compressible Neo-Hookean, incompressible Neo-Hookean, there's so-called nearly incompressible Neo-Hookean, the expression may be different. So what we have in the mechanics module should serve as merely an example. You need to make sure this expression is actually what you want to use, and if not, you're welcome to create your own material model in your own application. I've shown you how to do that in tutorial 2. Okay, so Kirchhoff and Neo-Hookean are the 2 hyperelastic materials. And for hypoelasticity, we support 3 different objective integration rates. We support the Truesdell rate, the Yeoman rate, and the Gray-Nagdi rate. And if you want to use the Rashid type of update, you can use the old tensor mechanics syntax. And then for Yeoman, I think this is what Abacus uses. Correct me if I'm wrong. I haven't used Abacus for many years. So, well, okay. So let me show you the actual input files for doing this. So if you go to tutorials 5, you can see many input files here, but there is only one main input file, which is called tension shear. So in this input file, I'm defining everything except the material model. So I have a physics block here. I have the mesh. I have the boundary condition, which is applying the tension plus a shear displacement. The executioner and aux variables for post-processing the force displacement curve, and I'm outputting Exodus and CSV. So as you can see, I have everything here except the material model, right? And for the material model is defined in the rest of the input files. Let's say if you want to define a small definition model, this is what you do. So you will need to specify the materials block here. It's an isotropic elasticity tensor, and it's linear elasticity. And you may wonder, do I need to somehow merge the 2 input files together in order to run the simulation? The answer is no. You can actually invoke the application with the -I option followed by multiple input files, and Moose will automatically merge those input files together. So I'll show you how to do that. So first is the path to your executable -I, and then the first one is our main input file, is the tension shear.I, now followed by the material model, which is small.I. So what Moose does is it will first do a pre-processing, merge the 2 input files, and then run the model as usual, as if it is a monolithic input file. So it will run the simulation and extract the force displacement curve for us for this small deformation material. And the output will be small, which is the name of the last input file suffixed by underscore out CSV underscore out.e. So the underscore out.csv file should contain all the post-processor values, and .e is the the complete output file in Exodus format. And we can do the same thing well, so now you should be able. Hopefully, you should be you can see how modular the design is, right? So if you want to change your material model, let's say to a Sinter-Kirchhoff model, all you need to do is to change the material block, right? So instead of, well, let's do a comparison here. If you want to do small deformation, you say compute linear elastic stress. If you want to do Sinter-Kirchhoff, you say compute Sinter-Kirchhoff stress. That's it, right? And then this is the pre-processing global parameter that gets substituted in the pre-processing stage. So for example, we have string equal to small, string equal to finite here. That's being substituted here. Right, so this is syntax. You want to specify some hyperparameters of your simulation. Well, I will give another example here. For example, if you say, let's say lambda equal to 4,000, and then you can say lambda equal to lambda. So this is useful if you want to, for example, group all of the parameters at the top of the input file instead of going through the input file here and there trying to figure out what parameters you're using. So this is useful for that purpose. Okay. And from the command line, if you want to select that different material model, all you need to do is to replace small.i with Sinter-Kirchhoff.i. And that's it. That's how you run the same simulation with the same set of boundary conditions, executioner, and so on, just with different material models. So this is useful if if your simulation campaign includes many different configurations, and a lot of them have many blocks in common. This is the recommended strategy for handling that. Okay, so now let me finish running all of the material models then. So that we just ran small and Sinter-Kirchhoff. Now let me run Neo-Hookean. And Truesdell, I guess, and Yeoman, and Greenogdy. So the syntax for objective integration is here. Yeah, I'll use Truesdell as an example. So you will define your own small deformation model and specify the objective rate you want to use to integrate it to be a large deformation model effectively. So this is the entry point. You can say the objective rate equal to Truesdell, or objective rate equal to Yeoman, or objective equal to Greenogdy. So this is the so-called hypoelasticity formalism. So after that, I think I included a script in the directory called plot.py. You can just execute the script. It will output an image comparing these 6 different material models, the resulting force displacement curves in X and Y directions for each of these material models. And I have some remarks here regarding hyperelasticity versus hypoelasticity. I will not try to comment on which one is better. There's got to be one that works for you. Choosing the suitable model for a particular material is essentially a matter of calibration. So what I view this is so practically speaking, you will have some experimental data, right? And if you believe, if you are a hypoelasticity person, you need to choose the objective rate that can best describe the set of experimental data. If you're a hyperelasticity person, you just need to choose the correct string energy density function that can best describe the set of experimental data. That's my view on this. The advantages of a hyperelastic formulation is not it has, you know, it can be derived variationally from a potential, and so it has all sorts of nice mathematical properties, and the time integration error is negligible because there's no time integration in hyperelasticity models. Advantages of hypoelastic formulations is that it's convenient. It's very convenient. Given a small deformation model, you need to change your code. You can directly just choose an objective integration method. It will behave like a large deformation model. And many common engineering materials have been calibrated using the hypoelasticity formulation. That's probably owing to some of the popular commercial softwares adopting the hypoelasticity formulation, I guess. And we do have a more detailed page documenting the known limitations of some of the hypoelastic formulations, and we also provide some recommendations. Okay, any questions? Any questions from the online attendees? If not, I will move on to the next tutorial, which is break. So we will not be taking a break. I mean, if everyone wants to take a break, we can.
You can't say that maybe there's some point.
Oh, is it already there? Okay, so I mean, why don't we take a break now and reassemble in 15 minutes, which is 3 p.m. Eastern time.
Oh, actually, before you go to break, so I have a really quick question.
Yes.
I missed that, but what are the units the software works in? I mean, can you change the unit, you know, the like unit lengths or something like that?
Yeah, very good question. Because that is the first question. That is the first question I expected. I was expecting this one to be the very first question.
Just
but
too
no
much
one has
information.
been answering this.
Yeah, too much information. Yeah.
Yeah. So let me try to explain this. I know if you're coming from a commercial software or some other software, you may be able to define units for different properties. So for example, you can choose whether the Young's modulus is in megapascal or Pascal or gigapascal or something like that, or kilopascal or non-SI units. That is not currently supported in MOOS. Okay, however, that is not equivalent to say MOOS. In MOOS simulation, you cannot use other unit systems. I know that probably sounds confusing. The idea is that as users, you are responsible for picking the unit system that's appropriate for your simulation, convenient for your simulation, and most importantly, consistently throughout the input file. So, for example, for all of these input files I've been showing so far, they use the consistent unit system, which is I think megapascal, millimeter, and second. That's the I think one of the most convenient unit system for me to work with. And so this results in Newton naturally. And so if you want to choose a different unit system, it's up to you. You just need to keep that in mind while setting up your input file and make sure all the quantities you specify inside the input file use the same unit system. For example, you cannot say, let's say lambda is, I don't know, 4 gigapascal and mu is 6,700 megapascal. That's not possible unless unless you do some custom treatment in your own application. I guess that's possible. And then if you do that, you should expect, for example, in your post processor, these values are also coming from the same unit system. For example, force will be Newton per millimeter. That's consistent with the unit system we've chosen.
Okay, so basically the how the mesh is defined will define the units, right? So like for example, if mesh is like, I don't know, goes from minimum is 0, maximum is 1, right? So and if I know that this is my I don't know, for example, a micrometer or a meter, so then it will define the what will be the dimensionalization of the rest of the equations. Is it correct?
That's not completely correct, because it determines the length unit, right?
Yeah.
But it doesn't really pin down the rest of them. I mean, you still have the freedom to choose a different time unit. You are free to choose a different unit for the force unit, right? Choose megapascal or pascal. It's still up to you. Although your length unit should be consistent with your mesh, and yes. However, that being said, you also have the option of rescaling the mesh after reading it into moves. So that's the powerful mesh generator system. I'm not going to go over in this tutorial. However, I want to show you. So for example, this sample mesh is in units of millimeter, but you can create a mesh, let's say sample meter, by chaining together these two mesh files with two mesh generators. So the first one is mesh file generator. The second one, I think, is called transform generator. So the input will be this sample mesh, and transform will be scale, and the vector value will be, let me see, when using translator scale, that's okay. So it's 1e minus 3, 1e minus 3, 1e minus 3, right? So this should change the unit from millimeter to meter.
Yeah, that makes sense. Thank you. And then, well, there's I guess I can find this in some kind of a tutorial for the mesh generation or something like that, right?
Yeah, I think I covered in the framework tutorial. So let me show you the website. If you go to the main MOOCE website, where you register for the training, you can see other trainings. And I mean, most of them are so if you see framework in the training title, the framework training, those capabilities belong to MOOCE framework and will be covered there. And today we are just covering the solid mechanics part of the.
Okay, yeah, that's a good, thank you.
And, I think we have planned to write a paper on the mesh generator, but I think I've lost track of that one. But do expect it sometime in the future. And you always have the option to go to the MOOCE documentation for a complete list of objects. In this case, navigate to mesh. You can see all the mesh objects you can use. It's a powerful system because you can chain different mesh modifiers together. It's just like you're using some.
Absolutely. That looks great. Yeah, thank you very much. Yeah.
Hey, I'd chime in about one thing about the units. So you're absolutely right about everything in a basic mechanics problem just being whatever the user chooses to use, you know, for their length and stress units. We do have applications that build on Moose that have models for specific materials and such that are based, that do assume that you're using a certain unit system. For instance, all the models in Bison are based on units of meters and pascals. And so, you know, sometimes there'll be relationships, you know, used in the models that need to depend on a unit system. So be aware of that. You know, if
yeah, thank you. Yeah.
And I'll also add there is actually in Moose support for assigning units to parameters. So, and there's like internal unit system conversion. I don't know that system all that well, but you can go in and assign a unit to something and then have it be automatic, or actually I think it's all just it may be handled like in parsing of an individual line, so you can give something in one unit and then tell it to convert it to another unit right there. So that's kind of a handy thing to use, but still, what Gary said about it, you needing to choose a unit system and using that across the board is still holds there.
Mm-hmm.
Yeah, I think what the last part Ben was referring to is probably the unit, this Moose unit system.
Yeah.
Yeah, so we do have this system for you to do conversion. So converting from unit to another is easy, and you can do that in your input file using this syntax. So you would say $sign and curly brace units.
Okay, yeah, that looks great actually.
But that's just a local conversion, you know, right for that input parameter, you know, where you're dropping that in.
Yeah, okay, I see. But yeah, so the main thing that basically, yeah, I see. So it's a little bit of kind of you have to always be cautious about what you put in. But I think that's a reasonable assumption because you know you cannot foresee what the users will really need, right, in generic kind of thing. But is there? I saw there was this like a function check dimensionality or something like that. So do you guys check the dimensionality when you build the like, for example, when you write the equation that the dimensionality on the left side corresponds to the dimensionality on the right, or it's not? I mean, I don't know. I just saw briefly, like when you were scrolling through this page, I think there was some kind of perhaps not. Yeah, I don't know. Well, anyway, so it's, yeah.
Yeah, that's probably an API for you know, for developers to check whether a user specified parameter is, you know, is a unit, a length unit, a time unit, or at the same time. So it's more developer facing rather than and just to be clear, we don't have any checks to make sure, for example, the left-hand side of the equation and the right-hand side of the equation share the same units. Because we simply don't have that information to begin with, right? Because at kernel level, we're just working with floating point numbers, right? We just don't have that information to perform the check.
Okay, yeah, thank you. Yeah, that's yeah. I was just curious, yeah. So
and I mean, building your own Moose-based application should open up a whole lot of possibility for you if you really want to add support for units, yeah, I think there's got to be a way to do that in your own application, right? It probably just requires some amount of effort, but I think it's possible.
Yeah. Thank you. That's good. Yeah.
Oh, and by the way, in case you didn't notice, if you go to the MOOS website, there's a gallery page of many fancy animations we've made for different purposes, but it's sort of a I think it's a good place for you to learn, how complicated can your applications become by building upon the MOOS framework. The most complicated ones are probably those like this flow streamlines in digital rock, some simulation of solid state battery charging, discharging, melt pool simulation, multi-scale geothermal simulation, some fluid dynamics and porous flow phase field simulations, things like that. This is contact. This is also contact. So as my point is, if someday you create your own MOOS-based application that has some fancy animations to show off to people in the community, feel free to add that to this gallery page. And as a bonus point, you can include a link to your application. So hopefully it promotes visibility of your work.
Hey, Gary.
Yes.
In this workshop, will you be talking about contact?
We will not. Sorry. We will not be talking about contact, unfortunately.
Okay. All right. But if we were to refer to any MOOS documentation, we can find relevant ones on the website, right?
I think all of the MOOS modules are decently documented nowadays. And so Ben Spencer in the chat, he is an expert in the MOOS contact module, and if you have questions, you can I guess you can ask him.
Okay, thanks.
Oh, there's a pop-up saying recording and transcription. Let everyone know they are being recorded and transcribed. Now you know. Okay, it's 3:01 now. Let's move on to the next tutorial. So I think I originally scheduled 9 tutorials for today. I think we're on track, which is unexpected, given that this is the first time I give this workshop. So tutorial 6 is on coordinate systems and planar formulations. I mean, 3D simulations are nice because we can mesh anything in 3D, but it's not the ideal solution for every scenario, because a lot of the engineering applications have some form of symmetry in it, and it's if you represent the geometry or problem description in a different coordinate system, it is oftentimes more convenient and more computationally efficient. So for that purpose, by default, everything is in Cartesian coordinates like x, y, and z. And we support 2 additional coordinate systems in the MOVE's solid mechanics module. Well, more generally speaking, I think they are supported at a framework level, but we have some, we spent some additional efforts to make sure that the mechanics models can work correctly in these other coordinate systems, including the axisymmetric cylindrical coordinate systems, which is, so think about the cylinder. We're just looking at a cross-sectional cut of the cylinder. That's R and Z, right? So the symmetry is in the theta direction. And the other coordinate system is the central symmetric spherical coordinate system. Its code name is R spherical. So it's a convenient coordinate system if you want to model a sphere or some structure with spherical symmetry using a 1D mesh. And for coordinate system Cartesian, we also support planar formulations. Well, I will explain what planar formulation does using this schematics. Well, let me make it full screen. So, I mean, in your elasticity course, you probably learned that you need to use different elasticity tensor for plane stress configuration and plane strain under plane strain assumptions. So that's doable in MOVES as well, in a slightly different way. I will explain. So what plane stress means is if your structure is very thin, such that we can assume that the stress remains planar. That's equivalent to saying the out of plane stress is close to 0, right? And for if we move towards the right of this diagram, that gets closer and closer to the plane strain assumption, where if your structure becomes thicker and thicker, then it's actually closer and closer to the assumption that the strain remains planar, which is equivalent to saying this out of plane strain is close to 0. So that's and anything in between should be able to be resolved using a full 3D simulation. So that's an assumption you need to evaluate as an analyst, right? So you need to decide whether it is appropriate to use this plane stress assumption or plane strain assumption, or you have to do a full 3D simulation. Well, that was a spoiler. So let me first show you how to choose different planar formulations from within the input file. So first of all, this is the 3D simulation we are interested in. It uses the same mesh we have been using so far. That was a 2D mesh, right? So here I'm adding an additional mesh modifier, which extrudes that 2D mesh to be 3D. And we have the physics syntax here for large deformation. And the material is a simple Sinfernot-Kirchhoff material. And for comparison purposes, we will be using the same material model, the same set of boundary conditions, and we will look at the force displacement curve. Well, in this case, I'm just comparing the final total reaction force along the top boundary when the displacement is equal to 2. Okay. Yeah, I think that's all I want to say about the 3D setup. Well, as you can see here, I'm using a parser to programmatically set the thickness of the 3D mesh. So in this case, I define a parameter h using the parameter n. Well, so n is basically the exponent. If n is equal to -1, the thickness will be 10 to the -1. If n is equal to 3, then h will be equal to 10 to the third. And then that h is used here to extrude the mesh. And now I can show you the error that we will get if we directly run the input file. I'm expecting an error. Okay, so the error is saying, can you see this? Yeah. How about now? Oh, yeah, okay. So the error is no variable n found for use in function parser expression. It gives you the exact line number where this is happening. It's here. It's because I'm defining h using n, but I'm not telling Moose what n is. To define parameters, you can not only do so inside the input files, but you can also do so from the command line. So this is actually a use case where that is really convenient. So we use the same command, but we say n is equal to -1 from the command line. So this is equivalent to saying n equal to -1 from within the input file. So we can do my point is we can do the same thing from the command line. So this is a useful capability when you want to use the same input file, but run that with a different parameter set without actually modifying the content of the input file. Okay, so this is running the solving the problem with thickness equal to 0.1 millimeter. We can do that with 1 millimeter, that's n equal to 0. For the interest of time, let me use 16 processors to run this. Yeah, it scales really well. You can see it's a lot faster, right? So when n is equal to 2 and n is equal to 3. So I've run the simulation 5 times from n equal to -1 to 3. So we have 5 outputs then. We have 5 CSV files with different n values. Well, by the way, this is my custom output file name. Let me show you. In the input file, I have file base equal to Cartesian 3D underscore h. You can see here I'm substituting the value of h as the question.
So you can the number for n in the input file and also in the command line.
Yeah, so command line will override what you have in the input file.
So there,
like you have this value here, and I like say I want H to be like 2 digits floating now just along. Actually, that's on 0.1000.
So the question was, can we fix the file name here? As you can see, it's 0.100001. I don't know if there's a good way of fixing that. I mean, I hope Daniel Schwan is here. He's the person to ask. So one way around this is to use n here instead of h, right? This will give you an exact integer, but I mean, such is life with floating point numbers. Well, actually, let me try. What happens if I say floor? This should give me the floor, the closest integer to this floating point number. And let me check what happens.
Oh, but that will be 0 because it's 0.1, right?
Oh yeah, what am I thinking? No, so that doesn't work.
Yeah.
Anyways, I hope that's just an annoyance rather than
you can round it up probably.
Yeah.
But that's
guys, let's forget about this. I would say this is a minor annoyance. So this is basically the same 3D simulation run 5 different times with different thicknesses. And now let me show you how to set up a plane strain formulation, which requires no input from the user. So this means that the plane strain is the default assumption we make for the 2D simulations. Right, so you just set up your 2D simulation as usual. If you don't do anything special, that's going to be a plane strain.
It's just assuming that displacement in the Z direction.
The displacement in the Z direction can be a homogeneous field. It can be it can be a homogeneous field with constant 3, but should give us 0 out of plane strain, technically speaking, right? Because, well, I guess what you said is correct.
I guess you can say there's no variation.
Yeah. Well, I don't know if we. So more strictly speaking, that is to say, the out of plane strain components are 0. So that's strain xz, yz, and zz, and zy and zx. That's yes, and I think that I think that's equivalent to what you said. So that's plane strain. For weak plane stress, I really hope to tell you that we can set it up directly from the physics syntax, but it's probably my fault when I was putting together this new system. I forgot to add an option for plane stress. So for now, you'll just have to expand the input file. But I assure you, I will submit a pull request right after this workshop so that you can do this directly from within the physics syntax. So just so you know how that will look like, it's we do have a parameter called planar formulation. The options are plane strain, weak plane stress, and generalized plane strain. So these are the options from the old system. So you can still use them if you are using the old system. But for the new system, I haven't added support for them yet. I will do so as soon as possible. But this is how you, well, I haven't talked about the additional setup for plane stress yet. So you need, well, so we call this weak plane stress instead of plane stress because, well, so let's first talk about plane stress. We really need to modify the stress-strain relation in order to ensure that the out-of-plane stress components are zero. That is not a modular definition because that requires modification to each and every material model we have. Instead, we opted to use a different method, which is the so-called weak plane stress method. What it does is it essentially introduces an additional Lagrange multiplier, which physically represents the out-of-plane strain. So that Lagrange multiplier enforces weakly that the plane stress condition is satisfied. So that is by introducing this additional variable string ZZ and this additional kernel. It's called total Lagrangian weak plane stress. So if you look at the source code of this kernel, it's surprisingly simple. It's just, well, let me show you the source code. Total Lagrangian weak plane stress. The residual is simply the is simply stress ZZ. It says, you know, stress ZZ should be 0. That's what it says. Though this is weakly enforced because this is being treated as one of the governing equations, and you get convergence towards plane stress as you refine the mesh. Okay, so this is how you set up weak plane stress. So now we have went through both planar formulations. Now let me run them. 2D plane strain and 2D weak plane stress. And I think, I'm not sure if I can. Yeah, okay. I have a script here called plot Cartesian.py. If you have run all of the previous simulations, you can use this script to generate a plot comparing these different formulations. So this is what I got. We've run the full 3D simulation with n equal to -1, 0, 1, 2, and 3. And as you can see, as the thickness is increasing, we're effectively switching from the weak plane stress condition to plane strain, where plane stress is this blue line and plane strain is this red horizontal line. And I think in the slides, yeah, I've run this. I've plotted this with more points on the with the full 3D simulation basically, and as you can see, it's a smooth transition. And so my point is, as an analyst, it is our responsibility to determine or to judge whether the planar which planar formulation is more appropriate for the specific simulation setup. Okay, so that was planar formulation. And remember, I also talked about different coordinate systems. So here I will show you a simple example for modeling this this geometry here. It's a, I don't know, it has this shape, and as you can see, it has this cylindrical symmetry, and so we can instead of running the full 3D simulation, we can run a 2D simulation using this cross-sectional geometry of the full geometry. And then all we need to do in the input file is to set this chord type equal to RZ in a mesh block. That is the magic option to change your coordinate system from Cartesian to axisymmetric cylindrical coordinates. And I don't think you need to change anything else in the input file. Right, you don't need to change anything else. This is the only change you need to make in order to in order to specify the cylindrical coordinate system. And now if I run the two simulations, well, I'll just show you the plot. If you run the two simulations and use the plotting script I provided inside the tutorial folder, this is the force displacement curve that you will get. Again, it's they should be identical upon upon mesh refinement. Okay, that concludes tutorial 6. Any questions? I haven't shown an example for a central symmetric spherical coordinate system, but it's the same idea. You change chord type inside the mesh block from the default to R spherical, and that will inform the most solid mechanics module to create the correct kernels and string calculators appropriate for this coordinate system. Okay, it seems like everyone is very familiar with coordinate systems. So now let's move on to tutorial 7, which, in my opinion, is a very important aspect of mechanics simulations. I think both developers and analysts should understand what volumetric locking is and what are its consequences and how we are alleviating volumetric locking effects in finite element codes in like moves. So standard 2D and 3D finite elements using a linear interpolation of the displacement field are not stable for incompressible and nearly incompressible deformation. So this could happen if your Poisson's ratio is very close to 0.5, or for example, if your material model is inherently non-compressible. For example, many plasticity models are only permitting a small part of volumetric deformation, and it mostly has a choric plastic flow, things like that. So it's important. What happens when, well, so I said the interpolation is not stable for this incompressible deformation, but what happens when it is not stable? You get wrong solution. So more strictly speaking, you not wrong solution, but you get suboptimal convergence order as well. So that's a more practical consequence. So two common methods have been developed to alleviate the effect of volumetric locking correction: the so-called F-bar approach and the so-called B-bar approach. So F-bar approach modifies the strain by averaging the volumetric portion of the string tensor, and then the B-bar approach additionally modifies the test function space to make the system symmetric. The B-bar method can be viewed as a subset of the F-bar method, and I think in most of the applications they are equally effective. But B-bar method, in fact, is more advantageous if your software utilizes symmetry. However, I don't think Moose is utilizing any symmetry information in the system, again, because it supports arbitrary multiphysics coupling, and you really cannot enforce that. And so we implemented the F-bar approach in Moose, which is just modifying the trial space. The solid mechanics module implements the F-bar approach to turn on stabilization. Simply set volumetric blocking correction equal to true inside the physics syntax, and it's actually more work behind the scenes, but this is all you need to do if you're using the solid mechanics syntax. And here's the conventional verification problem to examine the effectiveness of your stabilization implementation. So this is known as the Cook's membrane. So it has this membrane structure under plane strain assumptions. The left, so it has this geometry. It's a fairly regular geometry. There's nothing special. The left side is fixed, and on the right hand side, we are applying a vertical load in the y direction. Okay, now let me run the okay, so in order to turn on volumetric blocking correction, as I said, you just set volumetric blocking correction equal to true inside the physics syntax. I'm using the membrane mesh here. I use lambda and mu. Well, I use lambda and mu such that the material is nearly incompressible. And I use the boundary conditions as described in the schematics on the slide. Yeah, and then for post-processing purposes, we're extracting the y displacement at the top right corner of the geometry, which is this point right here. Okay, as you would expect. Well, so first of all, let's do an mind experiment, because this is Neumann BC. It is a traction load on the right. What will happen is the displacement should converge from below. By that I mean with a relatively coarse mesh, you should get a displacement value at the top right corner for the top right corner node, and as you refine the mesh, the displacement at the top right corner should increase and should eventually asymptote to the correct converged value, right? Upon mesh refinement, eventually we should be able to get there. And then this example is set up to tell you that if you're suffering from volumetric locking effects, that's actually not going to happen with mesh refinement, at least not with an acceptable amount of mesh refinement. So I've set up a script to automatically generate the membrane mesh with a different number of elements for each of the edges. So this is using the Gmesh Python API. You can do so. You can use the Qubit script if you have Qubit license, but this is how I would do it if you using this open source Gmesh API. So I automatically generate the mesh, and for each of the mesh, I call this input file. I call our application to use this input file to solve the problem, extract the displacement, and finally I plot the tip displacement as a function of number of elements per edge. So let me run this script. The second argument here is the number of processors I want to use. So in this case, it's 16. What? Well, let me run this input file to see what's going on. Hiding the error messages is probably not a good idea. Oh, unused parameter VLC. Oh, I see. Because I want to use VLC as a controllable parameter through the command line. So I think I'm expecting to put VLC here so that I can, from the command line, turn on and off the volumetric locking correction. So anyways, now it should work. So I'm generating mesh with different number of elements per edge. So in this first case, I'm turning on volumetric locking correction. And I'm using first order elements, which is Q4, quad 4. The second case, I turned off the volumetric locking correction, and I'm using first order elements, quad 4 elements. In the third case, still I turn off volumetric locking correction, but instead of first order Q4 elements, I'm using second order Q8 elements. And let's see what happens. It should generate this picture here, comparison.png. This is what we get. So the base case is Q4 without stabilization. Right? So because this is a nearly incompressible material, we see the effect of volumetric locking. So as we refine our mesh, it's not terribly effective in terms of getting us closer and closer to the correct solution. And when we use, so look at this blue line, which is Q4 with F-bar stabilization, with a reasonable amount of mesh refinement, we are able to converge fairly closely to the correct solution. And there's another case which is interesting, which is this green line here, using second order elements without any F-bar stabilization. It's also able to get closer and closer to the correct solution. I do want to comment here. In practice, I think there is nothing wrong with using second order elements if you want to avoid volumetric locking correction. However, it is less computationally efficient compared to using linear elements with volumetric locking correction. Right. So, for example, as you can see, it has the same level of accuracy with the same number of elements per edge. However, for second order elements, we need to solve a larger system of equations, and so the time to solution with Q8 element is not as good as Q4 element with stabilization. So that is the ideal scenario for using volumetric locking correction. Well, so this problem is set up so that to somehow exaggerate the consequence of volumetric locking correction to you. In practice, you will want to check, especially with linear elements, whether there is an effect of volumetric locking correction. And my recommendation is that since stabilization doesn't add too much to your to the computational cost, I would recommend you to turn this on whenever you can. That's my recommendation, basically. Okay, that's all I want to talk about for this tutorial for volumetric locking correction. Any questions?
If you repeat this with a larger ratio of length to mu, eventually the quad 8 without any stabilization will become pro-radical.
Eventually what?
Eventually your quad 8 will become quadratic elements
That's interesting.
You have to go to the fifth order before you start to really see things that are almost insensitive to operational math.
Yeah, okay. So there was a comment from Professor Doble just now for those of you online. He was saying that if we keep increasing the ratio of lambda to mu, which is effectively increasing, make the material more and more incompressible, the Q8 element without stabilization will eventually flatten out, meaning that it also suffers from volumetric locking. Eventually, if the material is sufficiently incompressible, I guess. So that's good information, I guess. Okay. Did we get any questions online? Okay. Okay, now let's move on to the second to last tutorial I want to go over today, which is structural dynamics and time integration. To include inertial effects or damping effects, we need to modify, actually extend the quasi-static balance of linear momentum to incorporate those effects. So that will be two additional terms. Density times the acceleration plus some damping coefficient times the velocity minus the divergence of stress equals 0. So these first two terms are new if you want to include inertial effects and damping effects. The solid mechanics module implements I would say three time integration schemes: the Newmark beta time integrator, the HHT alpha, the Hilbert-Hughes-Taylor time integration scheme, which is often referred to as the HHT method or HHT alpha method, and the explicit central difference time integration schemes. To turn on inertial effects inside your input file, simply replace quasi-static with dynamic. That will add the necessary kernels to incorporate those effects. Oops. Okay, so I just want to briefly go over the theory behind different time integration. So for Newmark time discretization, it is a widely used time integration scheme parameterized by two parameters, beta and gamma. So there are some commonly chosen parameters. When beta is equal to 1/4, gamma equal to 1/2, the Newmark method is unconditionally stable, which is often referred to as the constant average acceleration method. Well, I do want to comment here. Unconditionally stable doesn't mean unconditionally accurate, right? So those are two different concepts. So unconditionally stable means that you can solve it basically, but it doesn't guarantee that your simulation can give you the desired level of accuracy. In order to further reduce time integration error, you need to use a smaller time step still. Even though, with some larger time step size, you can solve it because it's unconditionally stable. But for example, you're solving a wave propagation problem. If you only sample a few points through the time axis, you're actually missing some information during your time integration. So that's a side note that I for whatever reason, I see many people confuse these two concepts. And when beta is equal to 1/6, gamma is equal to 1/2, it recovers the linear acceleration method. And when beta is equal to 0, gamma equal to 1/2, it is equivalent to the central difference method, though it's, technically speaking, it's still integrated implicitly. And for the HHT method, it's very similar. Well, it's in fact built upon Newmark beta method, but it additionally introduces some numerical dissipation controlled by the parameter alpha. So tuning this alpha, well, in fact, I think increasing alpha will increase the amount of numerical dissipation you introduce into the system. So when parameters are chosen appropriately, for example, so there's a hard constraint on, there's a hard bound on parameter alpha. It has to be non-negative, and it has to be smaller than or equal to 1/3. And then if you choose beta and gamma according to the value of alpha, you can still make the system unconditionally stable, and the system is at least second order accurate. And the third time integration method is explicit central difference. It's, I mean, the discretization is simple. It's central difference, right? What makes it important is so now if you look at the time discretization, the displacement now only depends on the previous solution. The system, so in other words, the system does not need to be implicitly integrated for us to get the solution to the next time step. That is significant because that completely removes the need of assembling the system of equations and doing factorization, applying preconditioning, and then use an iterative solver to do linear algebra to solve this. So it removes such cost. And so explicit method is, in some scenario, it is very efficient, and it scales very well to a large number of processors. And in Moose, we implemented the central difference method with 3 different solve strategies. So they are called consistent, lumped, and lumped preconditioned. So I would say that the lumped option is probably the most widely used option in other software packages. It essentially lumps the mass matrix with degrees of freedom wise. So that after you lump the mass matrix, your mass matrix becomes diagonal. And so solving the system of equations is as simple as inverting each diagonal entry of the Jacobian and multiply that with the right-hand side. So that's very efficient. And the other 2 methods are, well, they still assemble the full mass matrix, but they don't, well, if you use the consistent method, it still solve the system of equations using, well, it actually factorizes your matrix. So this will bring back the cost of an implicit solve, but it's very good for debugging purposes, right? So if you know your implicit solver definitely works, you can you can use this consistent option for debugging purposes. For example, whether your explicit integration is working or not. And then this lumped precondition is some middle ground between these two. So it uses the lumped mass matrix to form the preconditioner and use that as the use that for the linear solve. Okay, so now I want to demonstrate that with this simple problem, which is having a 1D bar. So consider consider a 1D bar with. Why do I comment this out? I don't think I need to. Anyways. Oh, I think why. I think I know. Yeah, so I want to. I think I want to tell you how to set up the boundary condition for this structural dynamics analysis, but I will shamelessly copy from what I have from my repository. Okay, so we have a Dirichlet boundary condition on the right, which is fixing the right hand of the 1D bar, and we want to apply an impact loading on the left-hand side. That's applied using this object called pressure. There's no difference between this pressure object and a simple Neumann BC if you only want to apply this on the undisplaced mesh, for example, for small strain problems, and if this is a 1D problem, or if it's multi-D, the surface is perfectly perpendicular to your, is perfectly aligned with your coordinate system. So this is similar to a Neumann BC, but the pressure boundary condition is implemented so that it accounts for any mesh deformation. So for example, if your surface is, if your surface area is changing, the amount of pressure should account for that, as well as the surface normal. So the pressure should always be applied along the normal direction of the surface. And then this function here prescribes the value, the magnitude of the pressure. So in this case, we will use this piecewise linear function to specify piecewise linear object to define the function. So the pressure will ramp up from 0 to 1,000 within 0.0 seconds, and then it will linearly ramp down with the same amount of time to 0. So it's simulating, I guess, an impact loading in some sense. And we use a simple linear elastic material. We post-process the displacement at the center of the bar, and later on we will plot that as a function of time. Well, so again, this is the base input file, and then we will specify different input files for different time integration schemes. So for the most basic Newmark beta method, so these are the parameters we need. This is, well, this interval here is telling us how often we want to output, right? So oftentimes for structural dynamic simulations, you want to use a fairly small time step size. As I said, the integration algorithm, like the implicit integration algorithm, is unconditionally stable but not unconditionally accurate. So you do want to use a fairly small time step size, and for that purpose, we don't want to clutter the output exodus file, because that will become unnecessarily large. And so we sometimes want to, for example, write the output once every 100 steps or once every 10 steps. That's what this interval parameter does for us. Yeah, and then for the record, for if you want to include inertial effects, you do need to tell Moose what the density is for the material. Okay, so this is the input file for a Newmark beta time integrator, and for HHT alpha is very similar. And for explicit time integration, though, for now, we will still have to specify quasi-static in the physics syntax, and then we need to include an additional kernel called inertial force, which is, well, this kernel is created by the physics syntax behind the scenes for us when we use implicit time integrator. But for explicit, we haven't set up the corresponding action yet, the syntax yet, and so we will have to do this for now. But in the near future, you don't need to do this. And in addition to all this, we should also specify the time integrator we want to use for the simulation. So to compare that with an implicit time integrator, well, here you don't need to specify anything because the physics syntax has done that for you. But for explicit time integration, for now, you still have to specify this time integrator inside the executioner block. So we will specify central difference. And as I mentioned, there are 3 solve types: lumped, here is consistent, and lump preconditioned, 3 different solve strategies. Okay, now we should be able to run these input files. So again, first of all, we need to specify the primary input file and then the input file defining the time integrator. We'll run the Newmark one first using 16 processors. I think I've set it to integrate all the way to 5 seconds. So let's wait for a while. Well, and actually for whatever reason, I've used 0.3 as the alpha parameter for HHT alpha time integration. So that should introduce a small amount of numerical dissipation. But for whatever reason, let me use a different value of alpha here, for example, 0.2. Let's see if it works. And actually, I think for such a small problem, using 16 processors probably actually slows down the computation because the overhead for communication among different processors is I think it has taken over the majority of the cost actually. So explicit consistent. Well, let me use a smaller number of processors. Well, for explicit, one thing I forgot to mention is that it is not unconditionally stable. There is a limit on the maximum timestamp size you can use, otherwise it will explode. And usually that bound on the maximum time step size is smaller than what you need to get an accurate solution. So that is oftentimes referred to as a trade-off for explicit time integration. And if your system is very stiff, like for some of the plasticity models, I think it's extremely stiff. And if that is the case, what we found is that an implicit time integrator is actually more efficient than an explicit time integrator, because even though it takes more time to solve each time step, it is able to use a much larger time step size than what's required by an explicit time integrator. So again, it's probably the analyst's responsibility to decide what's the most appropriate time integrator to use. And then, however, I mean, not being said, explicit time integration does have another advantage, which is that you don't need to hand code the Jacobian anymore. You can just define a residue and it'll integrate the system of equation for you in time. That is sometimes useful when you want to do rapid prototyping, or if you're running into some weird convergence issues with implicit solver. However, so right now, since Moose is using automatic differentiation, AD, we automatically extract the Jacobian information from using forward mode AD. It's actually less obvious to me why you would want to use an explicit time integrator for rapid prototyping. So that's just some additional considerations for you. Okay, so the last one, not the last one, the next one I want to run is lumped. So this one should be really, really fast because there's literally no solve going on. It's just a simple element component-wise inversion. So as you can see, it's really fast. And the last one is lumped preconditioned. Oh, lumped precondition. Okay, and I think I have a script to plot all the results and compare the. Yeah, this is what you get with. So this is the comparison between Newmark and the HHT alpha, and because so remember HHT alpha introduces some numerical dissipation through that alpha parameter. And so you can sort of see that here, right? If you look at this region, the curve is somewhat smoother with an HHT alpha time integration than the Newmark beta method. And actually, this is interesting because I think I used alpha is equal to 0.2 in the simulation I ran just now, and in the slides, I think I used alpha equal to 0.3. And well, you can sort of see that here. There's more dissipation going on with a larger value of alpha. And then the same comparison can be made for explicit methods. Well, this is just a verification. They should basically overlap. Okay, that concludes the tutorial number 8. Any questions? If not, we will move to the last example of the day.
Here, I just missed where you said So the idea that the diagonal mass matrix is a pretty good preconditioner for system. Is that how that works?
Yeah, that's the idea. And another consideration is compared to the consistent strategy, where we are actually factorizing the mass matrix and solve the system. I mean, numerically, what's going on is most of the effort has been spent on computing the factorization, right? And so the idea is if we use a preconditioner that is known to be effective for this type of system, which is, you know, lumping the mass matrix and set up a diagonal matrix as the preconditioner. Why don't we use that? And as with that preconditioner, we can still perform a linear solve. But the idea is now we've skipped the expensive part of actually, you know, computing the factorization. It should still speed up the computation by a fair amount. Oh, and for the record, for those of you online, the question just now was asking me to elaborate more on the on what we do for the lump preconditioned solve type, and I was just trying to explain that. If there's no other question, we will move on to tutorial 9. The homogenization constraints. I know this is, sorry, give me 1 minute. I'll grab some water. Okay, sorry about that. For this last tutorial, we will be learning how to set up homogenization constraints. So this is a very useful system if you are interested in well, homogenization, right? So to model micro and mesoscale RVEs, it is often desired to apply constraints on the RVE averaged strain and or stress components as the, you know, ad hoc boundary conditions. The solid mechanics module features this homogenization system for setting up such constraints. You can do that with, I think, 2 lines of code inside the physics syntax. But here I want to go into a little bit more details on how we implement these homogenization constraints. So the theory largely follows from this Danielson's paper from 2002. For small deformation, the constraints are of the type of, you know, the domain average of stress equal to some prescribed value, or the domain average, the strain is equal to some prescribed value. And for large deformation, it looks the same, but we decided to apply the constraints on the first Piola-Kirchhoff stress tensor and the deformation gradient. Well, you can of course inherit from the Moose constraints and implement your own constraints and use what we have done in the framework as an example and a good starting point. More on the theory. So just now I talked about what the constraints are. And the homogenization system introduces an additional affine displacement field where you can decompose the displacement into the micro displacement field and the macro displacement field. The macro displacement field is what is used to satisfy the homogenization constraints. So this is a simple KUBC type of constraint. For small deformation, the macro gradient tensor G is symmetric. Well, because the strain tensor should be symmetric. And for large deformation, it is not, because we are applying a constraint on the deformation tensor. The deformation on the deformation gradient, sorry. The deformation gradient that follows as, well, so the usual definition is identity tensor times the gradient of displacement. But in this case, because we decompose the gradient into a micro and macro field, it can be expressed as identity plus the gradient of the micro displacement plus the deformation gradient tensor, which is the constraint we apply. Then the following constraint residues can be defined, so which is basically saying the difference between the prescribed target for the homogenization should be equal to the domain averaged stress. And in the case of a strain constraint, it's the same expression but applied on the deformation gradient tensor. And as I promised, you can do that with 2 lines of code inserted inside your input file. So those 2 parameters are constraint types and targets. So let me show you how to do that. Well, so let me first explain what each of these options, each of these option it does. So for constraint types, it is a vector of 9 strings or enums. So each of the string should be taking value either string, stress, or noun, indicating that the corresponding component of the tensor should be string controlled or stress controlled, or no constraint should be placed on that particular component. And there will always be 9 components in the syntax, right? And we will always follow the column major convention. So which is, so speaking of components, that is XX, YX, ZX, XY, YY, ZY, and XZ, YZ, and ZZ. So that's the convention. You can find all of these in the documentation. And the second parameter is called target. So for each of the constraints that is not noun. So if let's say if you have some strain and stress constraints, you should have the same number of targets. They basically specify the prescribed values for each of the combined constrained components. And let's try to set up this constraint problem described here. So this is a 4 material system, right? So it's a simple square block, but divided into 4 different materials. Well, even though all of them are using the new Hookean material as the formulation, they have different material properties. So they have different lambda, different mu for each of the material. Just so that I can demonstrate this homogenization constraint is working correctly. And let's say we want to prescribe the homogenized deformation gradient in the x-axis direction using this sine cosine function. And similarly, we apply sinusoidal constraint on the first Piola-Kirchhoff stress, the xy component and yy component. And for the yz component, for whatever reason, let's make it 0. So that's the target constraint we want to prescribe. And let me show you how to do that inside the input file. Okay, so these are indeed hidden. So first of all, I will define 3 functions. So remember, How do I move it? There we go. So let me first define a function for the x-axis constraint. So that's f(x() type equal to parse function expression equal to 1 plus 0.1 times sine of 20t plus 0.1 times cosine of 15t. Similarly for pxy. 100 times sine of 13t plus 150 times cosine of 9t. And for pyy, let's say we want to do minus 70 times sine of 9t minus 130 times cosine of 25t. So now I have all the necessary functions for me to specify the constraints. Then in the physics block, as I said, the first parameter is constraint types, right? Because it's column measure. The first one is x-axis, so it's string constraint, and then y-axis is string constraint, and the z-axis has no constraint, and pxy has stress constraint, pyy is stress constraint, and then the rest of them is just no. And then for the targets, because we have 4 constraints here, with 2 of them are string constraints, 2 of them are stress constraints, we need to specify 2 values here. So you can either provide a number or a function. So it's f(x(), fyx is just 0, and then pxy, and then pyy. So that's how you set this up. The rest of this concerns with definition of the material. And in addition to the, well, so there's one thing I forgot to mention in the theory. So for this homogenization to work, the displacement field has to be affine, or in other case, the total displacement should be periodic. We need to apply periodic boundary condition, periodic constraints on the displacement x and displacement y. And if it is 3D, you need to constrain on the z direction as well. And in addition to the periodic boundary constraint, you also need to fix some selected set of nodes so as to remove the rigid body modes, basically. Yeah, so that completes the setup of the homogenization constraint. Now I can run this. Whoops. Oh, I think I called it EXX here for whatever reason, but I'll call it FXX. I think I called it PXY here. UX is 0. This is PUI. Okay. So as you can see here, we have introduced some, because we have introduced some scalar kernels, those are automatically treated as post-processors because, well, they are basically a single number from the entire simulation result. And so, so these scalar variables are called hvar 0 all the way to hvar 3, because we have 4 constraints here. 2 of them are strain constraints, 2 of them are stress constraints. And so you can visualize in pair view, but I'll show you the animation I've made beforehand. Well, so first of all, I want to show you the evolution of the homogenized strain and stress, just to show you that it is working as intended. So we have a black solid line, that is the target value we prescribed, and the hollow circles are the homogenized components that we post-processed from our simulation. And you can see that for all of the 4 components, they have a perfect match. And then those A, B, and C, D, A, B, C, D dashed curves, these are the corresponding homogenized quantities for each of the domain. Remember, we have domains. I'm naming them A, B, C, and D. This is to show you that in order to satisfy the homogenization constraint, we do not need to satisfy these constraints for each and every subdomain. Instead, since the constraint is placed on the entire RVE, they can have fluctuations in order to accommodate the overall homogenized strain and stress. Okay, and I have an animation here showing the sinusoidal movement of the RVE, just for fun, I guess. Yeah, and this is what's going on. And in fact, it's not a trivial task if you want to directly apply the boundary conditions. You know, I'm not sure if there's any way of specifying. Well, there's probably some way, but it will be very complicated to directly apply Dirichlet boundary conditions on the 4 boundaries. And during the animation, you can sort of see that the effect of the arbitrary node we picked to remove the rigid body nodes here, which is these 2 points. So they will stay in place during the entire simulation, but you know, they will have some negligible effect on the result. So you need to pick those nodes appropriately so as not to introduce too much of a constraints on those nodes for the purpose of removing rigid body modes. Okay, so that so that should conclude the workshop for today. And I do want to mention that what I covered today, it's the absolute fundamental of the solid mechanics module. And if you go to this online documentation, you can see a comprehensive list of the advanced features offered by the solid mechanics module, including some commonly used inelastic models, the cohesive zone method, smear cracking, fracture integrals, some commonly used structural elements, frequency domain analysis, as well as IGA. I would say feel free to ask questions related to these other advanced features in the Slack workspace as well, and we can continue our discussion there. So with that, I think we can wrap up the day one of the tutorial then. So today we went over the fundamentals of the solid mechanics module. We covered the usage of the solid mechanics syntax. We've actually at the very beginning implemented our own version, own simplified version of the solid mechanics module, just for us to understand what it does behind the scenes. We've introduced and compared the several different small and large deformation models, especially hyperelasticity models versus hypoelasticity models. We've learned how to specify coordinate systems and planar formulations for our simulation. We learned the effect of volumetric locking and the corresponding strategy to alleviate that. We've also went over simulations for structural dynamics and simulations with homogenization constraints. So tomorrow, we will demonstrate solid mechanics related multiphysics coupling. And for that purpose, I will use phase field fracture as an example. So tomorrow we will implement our own phase field fracture model in Snail from scratch, right? So that sounds like a daunting task, but I think it's doable within one day. As such, so today is more like analyst facing. I'm teaching you how to set up the input file and what each of the capability does. And tomorrow it will be more developer facing, where we will actually be writing a lot of source code. So I would say try to sort out any installation issue, if any. And if you have any question for any of the content from today, make sure we clear that out before tomorrow's workshop so that we can directly dive into coding. And that's it. With that, I'll wrap up today's workshop. And is there any last minute question? Do we have any question from the online audience? If not, I will sign off here.
Thank you, Gary.
Thank you.
Okay, thank you. Bye.
Bye-bye.